Methylene blue, biohacker's delight, or playing with fire? This is the answer to the July CMJ Masterpass winning question, which is about whether methylene blue is good for general mitochondrial health. And this is the short answer. Methylene blue is a strong antimicrobial and disinfectant. In the presence of phototherapy, it is a stronger antimicrobial and it can be used against tumors as well as pathogens. It has medical uses for visualization as a dye, prevention or treatment of post-surgical complications. It treats malaria and certain forms of methemoglobinemia. It produces hydrogen peroxide, and it can rewire the respiratory chain in the mitochondria to get around specific toxic or genetic impairments. It's a strong monoamine oxidase A inhibitor, which means that whether you feel better on it is actually a completely unreliable guide as to whether your energy metabolism is being improved. Outside of the standard medical applications and contraindications, it likely has value for vasodilatory headaches and for the treatment of respiratory chain disorders. But it is not a general health tonic, and it does not provide general support to the mitochondria. In fact, there is evidence that if you need it, it helps you. But if you don't, it hurts you. Okay, so that's the short answer. Now let's dig into all those details to get the long answer. So in this episode, you're going to find the origin of methylene blue. You're going to learn about the entry of methylene blue into medicine, from malaria to many uses in medicine. And we're going to talk a lot about how methylene blue works. We're going to talk about methylene blue as a redox-reactive dye, the blue bottle experiment, methylene blue radicals, photoexcited states, and demethylated metabolites, how methylene blue can oxidize and reduce many different targets, how methylene blue can rewire the mitochondrial respiratory chain, but why rewiring the respiratory chain does not make it better. We're going to talk about methylene blue increasing hydrogen peroxide and how hydrogen peroxide kills microbes, has hormetic benefits, and yet is still ultimately toxic. We're going to talk about methylene blue causing redox cycling of hemoglobin, how it's a strong monoamine oxidase A inhibitor, how it's a nitric oxide synthase inhibitor, and we're going to wrap these up into some mechanistic conclusions that we can use to then look at the health effects. Among those, we're going to examine the question number 1, is methylene blue fundamentally hormetic? Number 2, why did methylene blue fail in the Alzheimer's trials? And we're going to look at a very worrisome side effect that we can then tie to a piece of data from an animal experiment. We're going to talk about why methylene blue helps or hurts depending on whether you need it, natural alternatives for hormesis and rewiring the mitochondrial respiratory chain, and then finally, we're going to arrive at who should use methylene blue. So let's dig into those details right now. Methylene blue is a synthetic dye that in the solid state appears in a greenish color when it's in its purest form, but generally in solution and in most formulations takes on its characteristic bluish color for which it's named. Methylene blue does not exist in nature. It was first synthesized in 1876 by the German chemist Heinrich Caro from dimethylaniline, a derivative of benzene, which is naturally found in petroleum. And at that time, it was derived from coal tar. Methylene blue is still synthesized to this day from petroleum-derived dimethylaniline. August Wilhelm von Hofmann was another German chemist who had laid down the basis for the synthetic dye industry in the 1840s by studying the contents of coal tar. In 1856, his student William Henry Perkin discovered the first coal tar dye, mauve. Within 2 years, Perkin had established a factory to produce mauve in London. Coming back to Caro got his start in calico printing, which is a technique that was used for semi-automating the imprinting of dye patterns on calico, which is a form of cloth made from cotton. Caro turned out to be a brilliant chemist and inventor, and used his inside knowledge of the textile industry to systematically generate synthetic dyes that would attain widespread use. One of his first achievements was to develop a more productive means of synthesizing mauve so he could compete with Perkin. Caro formed a partnership with the research chemist Alfred von Baer and tasked him with synthesizing indigo, the holy grail of the synthetic dye industry. This would break the British global monopoly on the natural indigo pigment, known as the king of dyestuffs, which was produced in vast quantities from plantations in colonial India. Bayer's 1905 Nobel Prize in Chemistry was awarded in part for his successful synthesis of indigo in 1897. When Caro and Bayer first met, Bayer had been studying the production of dyes known as phthalenes, derived from phthalic acid, which is also the source of phthalates used today in the production of plastic. Bayer had produced fluorescein from this, which today is used as a food additive, yellow number 7, as a contrast agent in the eye doctor's office, and in the laboratory detection of blood concentrations of thyroid hormone in the labs. Caro introduced 4 bromine atoms into the fluorescein molecule to make the yellow-red dye that he named eosin. He chose this name based on the nickname Eos of his friend's sister, Anna Peters, on whom he had a crush in his youth. Today, eosin is used in red ink. Together with the wood-derived natural dye hematoxylin, it's used to stain cells and their components, known in the study of tissue slices or histology as hematoxylin and eosin, or H&E staining. The white blood cells, eosinophils, are named for their love of eosin. That is, eosin stains these cells red. Few may realize that these cells are, in name, competing with Caro for the elusive Anna. One wonders, then, if allergic reactions are characterized by eosinophilia simply because the eosinophils are rising up to finally win the spirit of Anna Peters with some grand, perhaps romantic in some lights gesture. Caro had tasked Bayer with studying the basic science of nitroso reactions in which nitrogen is added to organic chemicals. In 1876, the French chemist Charles Loth synthesized Loth's violet, but he couldn't make very much yield out of it. So Caro then utilized Bayer's research on nitroso reactions to very quickly develop a higher yield way to make Loth's violet, and in a slight modification of the process, he also stumbled his way into the invention of a blue pigment that he named, you guessed it, methylene blue. The following year, in 1877, Caro obtained for methylene blue the first ever German dye patent. In 1878, he patented it in the United States. According to the US patent, the principal benefit of methylene blue was that, unlike previous synthetic dyes, it could be combined with metallic derivatives of tannic acid to become insoluble. This would allow fabric to be dyed blue without the dye being easily washed out. So remember, when we talk about the health impacts of methylene blue, that we're talking about something that was invented for the principal benefit of creating blue coloring in clothing and tapestries that would not come out in the wash. All right, now we get to the entry of methylene blue into medicine. The entry of methylene blue into medicine was catalyzed by the German physician-scientist Paul Ehrlich, who won the 1908 Nobel Prize in Physiology or Medicine for his work on immunity. Ehrlich should be known as among the fathers of immunology and as the father of modern pharmacology. He coined the term chemotherapy himself, which at that time did not have the cancer-specific meaning that it has today, and it simply meant the treatment of diseases with chemicals. He was the first to propose a well-known and received articulation of ligand-receptor relationships, wherein drugs are conceived as things that bind to specific receptors that then carry out specific modes of actions inside cells, which is the basis of modern pharmacology. From the time that he was in med school, he envisioned discovering a, quote, magic bullet that would, through such molecular mechanisms, kill both tumors and microbes while leaving the human host unharmed. As the German synthetic dye industry expanded for the sake of the commercial textile industry, the parallel use of synthetic dyes as stains in medicine expanded alongside it. The dyes were used to enhance visualization of biological materials under microscopes. Dyes had been used to stain blood cells as early as 1865 by W. Erb, but Ehrlich took the lead in this realm by 1877. Staining slides of blood enabled him to newly discover mast cells and different types of anemias and leukemias. Ehrlich was so obsessed with studying staining techniques that his hands, clothes, and surroundings were always visibly stained. Ehrlich began classifying synthetic dyes according to their chemical composition and showed that chemically different dyes would stain different types of cells and subcellular components. In 1879, he made a stain from methylene blue and the synthetic red dye fuchsia and showed that it would stain red blood cells and eosinophil granules red, nuclei deep blue, white blood cell cytoplasm light blue, and imaged for the first time ever, neutrophil granules were stained dark violet. In 1880, the French military surgeon Alphonse Laverin showed that malaria, named for mal-aria, bad air, was actually caused by a parasite. And in 1888, the Polish physician Czesław Ivanovich Chenzinski showed that the malarial parasite could be visualized using a stain made from methylene blue, water, eosin, and alcohol. The Italian researchers Celli and Guarnieri soon after developed a modification of Chenzinski's stain, and Ehrlich took their modification, and he showed that not only could you stain the malaria parasite after you had taken dead cells and made a slide out of them, but you could take fresh blood out of a human, you could put the stain on it, and while everything is still alive, you could stain the live parasites. And you could also inject the methylene blue directly into an animal that was infected with malaria, take out its blood, and the parasite would already be stained. And so, seeing that the dye selectively accumulated in the parasitic cells and in the human cells that were infected by the parasite, suggested to Ehrlich that, this may be the magic bullet. It may be the thing that kills the pathogen without killing the human host. So, on the basis of those preclinical observations that malaria turns blue when it's given methylene blue, he got together with the German pathologist Paul Gutmann, and he successfully treated 2 malaria patients with methylene blue in 1891, going off a hunch that turning blue meant the thing would die. Okay, so with this, methylene blue passed from being the first synthetic dye with a German patent to being the first synthetic drug ever administered to humans. And this event was, in turn, the dawning of the era of modern pharmacology, in which chemists take derivatives of coal tar and petroleum and synthesize patentable drugs to be the treatments of all human maladies. Fast forward to today, and we have gone from malaria to many uses in medicine. Briefly, this is what that trajectory has looked like. By the turn of the 20th century, methylene blue had become widespread in medicine as a topical and internal antimicrobial, as a visualization tool, and since it turned the urine blue as a marker of compliance. So methylene blue is added to antipsychotic medications so that psychiatrists could give the medications to their patients and then could look at their urine and could know they were on their meds if their urine turned blue. Now, this led to the serendipitous discovery that the dye itself appeared to have pain-killing and sedative activity in various forms of psychosis. Methylene blue, alongside this, also became a universal feature of laboratory equipment, used as a disinfectant, as a visualization tool, and in all sorts of experiments where its chemical behavior came into play. In the 21st century, fast forward to today, reviews attribute to methylene blue the following medical uses, which have various levels of evidence supporting them. Number one, inherited methemoglobinemia. This is a genetic condition leading to the oxidation of iron within hemoglobin, preventing it from carrying oxygen. It's treated with 50 to 250 milligrams of methylene blue taken once per day for life. And then there is acute methemoglobinemia. This is acquired, and it can be caused by a number of things. It could be overexposure to topical anesthetics, in particular benzocaine and prilocaine, to nitrates, to the dye aniline, ironically the petroleum derivative that ultimately yields methylene blue through dimethyl-aniline, or the antibiotic dapsone. Acute methemoglobinemia in general is treated with intravenous methylene blue using 1.3 milligrams per kilogram body weight once or twice over the course of 20 minutes. This obviously is in this context of an emergency room. However, this treatment can be less successful for aniline, and it's contraindicated with dapsone. Ifosfamide-induced neurotoxicity. This is a controversial one. Ifosfamide-induced neurotoxicity occurs as a complication of the chemotherapy agent, in this case, actually in the modern sense of treating cancer, ifosfamide, which is labeled for cancers of the testicles, ovaries, and thymus, but is also used off-label for cancers of the cervix, lungs, bladder, and for soft tissue sarcoma, Ewing sarcoma, and lymphoma. The neurotoxicity can be rescued with 50 milligrams of methylene blue taken 4 times daily, orally or intravenous, but its efficacy in this context has been questioned. So whether it actually works is not clear. According to reviews, urinary tract infections in elderly patients can be prevented with methylene blue at 65 milligrams taken orally 3 times a day. And vasoplegic shock actually has quite a bit of strong evidence in the acute but not mortality context. Vasoplegic shock is characterized by severely low blood pressure, and it can occur in sepsis after cardiothoracic surgery or following burns and trauma. When resistant to the administration of adrenaline, methylene blue is used to raise blood pressure with 200 milligrams intravenously over 1 hour, followed by an infusion of 0.25 to 2 milligrams per hour. That infusion dose can also be used before surgery or during surgery in order to prevent vasoplegic shock. Malaria, methylene blue fell out of use. Some people say because it was less effective than later drugs. Other people say because people didn't like turning blue when they took it, but it has made a comeback in the treatment of malaria. And malaria can be treated with 12 milligrams per kilogram body weight twice per day orally for 3 days. Lower doses can be used in combination with other drugs in those with glucose 6-phosphate dehydrogenase deficiency, which is considered a contraindication for methylene blue, but some argue that it's safe at low doses. But although it made a comeback for the treatment of malaria, it was circa 2010, it actually started to decline because the safety requirements to minimize contamination of methylene blue using good manufacturing practice guidelines made its price go up 100-fold, which made its use for malaria among the world's poor decline. And the safety achievement is questionable because the predominant contaminants were copper, chromium, water, and demethylated metabolites of methylene blue that actually might be responsible for some of its therapeutic effects. So in the literature, you'll find it questioned whether this was not a net negative outcome to raise the cost of a drug that is otherwise safe to use for the world's poor against malaria. Now, there are also various claims that it can be used for priapism, which is prolonged erection of the penis, topically for itchy anus, as an oral, topical, or locally injected sensitizer for photoinactivation of viruses, fungi, bacteria, and tumors. And these include antibiotic-resistant staph, Hep C, HIV-1, herpes simplex, nail fungus, melanoma, and basal cell carcinoma. And phototherapy for psoriasis, management of chronic kidney stones, neurotoxicity from the overconsumption of ackee fruit, as a dye for visualization during operations, as a general topical disinfectant. There are some studies from the 1930s suggesting it may benefit catatonic dementia and epilepsy and act as an antidote to carbon monoxide poisoning and to cyanide poisoning. And recent animal studies suggest it's a useful antidote for poisoning with hydrogen sulfide, sodium azide, and rotenone. It's currently under investigation as a possible benefit in Alzheimer's, although the trials have largely been failures. And it strongly accumulates in melanated tissues. So internal use of methylene blue, I would speculate, combined with phototherapy or sunbathing, is probably highly effective against melanoma. But this also seems to suggest that this could raise the risk of skin damage in people with dark skin, since more methylene blue would be expected to accumulate in healthy dark skin than in healthy light skin. Now let's take a look at what meta-analyses say. Meta-analyses are generally done when there's a large enough body of evidence to do them, so they shouldn't be looked at alone, but they're a good way of getting a bird's eye view of what the efficacy data look like. Meta-analyses take many different studies on the same topic, and they pool the results to look at the general overview of what does it seem like the net effect is. And the meta-analyses that have been done on what is meta-analyzable about the tens of thousands of papers published on methylene blue basically say as follows. It is effective at increasing blood pressure, heart rate, and decreasing the risk of renal failure in vasoplegic shock. It is probably not effective for ifosfamide-induced neurotoxicity. Meta-analysis of 9 randomized studies and case reports suggest that hydroxycobalamin, which is a form of vitamin B12, is just as effective as methylene blue in the context of vasoplegic shock, but the evidence base is larger for methylene blue, smaller for vitamin B12. Used as a stain, it can help better identify lymph nodes from sampling when assessing the extent of colorectal cancer. It's also effective in combination with other dyes to identify cancerous lymph nodes spreading from breast cancers, and it can help detect abnormal growths in ulcerative colitis. Further, it can be used as a dye to help visualize the swallowing process during swallowing examinations. However, it does not enhance biopsy procedures of small intestinal abnormalities in Barrett's esophagus, where the esophagus is damaged from chronic acid reflux. Treating fresh frozen plasma with methylene blue reduces fever reactions in transfusion recipients, and methylene blue catalyzed phototherapy is effective for superficial fungal infections, including in the mouth and throat. Pooled with other photosensitizers, including riboflavin, collectively, photosensitizers, including methylene blue, are able to reduce bacterial counts in denture bases. Methylene blue does enhance phototherapy treatment of gum disease in smokers, and it is effective in general against tooth decay causing biofilms. However, gargling it does not enhance phototherapy against, quote, oral potentially malignant disorders, which is when it looks like you might have something that could turn into mouth cancer. And it is somewhat less effective than 5-aminolevulinic acid in phototherapy for lichen planus, an autoimmune condition affecting the skin, hair, nails, mouth, and genitals. And although it's less effective than the alternative, they're still both effective. When injected into the discs between vertebrae, it reduces discogenic back pain. And then finally, methylene blue used locally at the site of a surgery can reduce the risk of tissue adhesions that form during the healing process. All right. And in general, what we can say about negative effects is as follows. So in sheep, the dose required to kill 50% of the animals, the lethal dose 50%, or LD50, is 42.3 milligrams per kilogram body weight intravenously. It seems that intravenous methylene blue is more toxic than oral methylene blue because in dogs, up to 2 grams per day is tolerated orally, but injections of 0.5 grams per day are lethal. That was shown in 1929. In humans, early toxicology studies showed that 7 milligrams per kilogram intravenously can cause severe gastrointestinal symptoms. In the human trials with doses of 69 to 250 milligrams per day for 6 to 15 months, the most commonly reported side effects, and these are very common, are diarrhea and altered urination. These trials have 20 to 40% dropout rates. Methylene blue is a monoamine oxidase A inhibitor. That means it carries the risk of serotonin toxicity, hypertension, and psychiatric dependence. If you're on 100 milligrams of methylene blue a day, you are on a psychiatric drug, and there is some possibility that you'll be addicted to, that you could become tolerant, dependent, or addicted to the antidepressive and anti-anxiety effects of that. Contraindications include glucose 6-phosphate dehydrogenase deficiency, use of SSRIs, hydroxylamine toxicity, renal failure, and caution should be used in cases of methemoglobinemia of various causes, especially dapsone and aniline. And cyanide poisoning is and nitrate poisoning is controversial. There's cautions against using it in that case, but it doesn't seem like there's a lot of evidence that it's dangerous. And there is recent evidence in animal experiments that it's very effective against cyanide toxicity. And then finally, methylene blue can make a pulse oximeter inaccurate because the pulse oximeter is looking at the color of your blood, and methylene blue will change the color of your blood. All right, so that's at a bird's eye view what the literature looks like in the context of reviews and meta-analyses. Now, if we dive deep into the mechanisms, what can we say about how methylene blue works? And we're going to rewind back in history a little bit to look at the development of this, because our basic understanding of how methylene blue works in the context of complex human physiology is best suited by understanding how it works outside the human body as a dye. So in 1925, Mansfield Clark, who was responsible for introducing the use of the pH and oxygen electrodes, co-authored a massive paper on methylene blue with two other chemists, Barnett Cohen and H.D. Gibbs, who all worked for the United States Public Health Service. In that paper, they wrote the following: "We failed to find any common principle underlying the manifold uses of methylene blue as a therapeutic agent. And the nature of some of these uses leads us to wonder whether any principle was considered." In other words, the use of the dye in medicine up to that point had been based on speculation and fortuitous accidents, and not on a bottom-up understanding of what the dye was actually doing. They suggested that their own work on its electron transferring properties, quote, should be useful to the pharmacologist, end quote, who was trying to understand why the dye had therapeutic value. Methylene blue is a redox-reactive dye. One of the early observations on synthetic dyes was that many of them could be rendered colorless and therefore white by electron donors, although they didn't know that it was electron donation that was happening. In retrospect, we know that what was doing that was electron donation. The donation of an electron is known as reduction. The theft of an electron is known as oxidation. Together, the transfer of an electron is known as a reduction-oxidation reaction, or for short, a redox reaction, from read, reduction, oxidation, redox reaction. These processes were named after early observations before it was understood that what was happening was electron transfer. Those observations were that what was generally talked about as the degradative processes of oxidation happened when something was exposed to oxygen. So that was called oxidation. And then what was also realized was that if you did the opposite, you would reduce the mass of something, which was thought to happen because oxygen left that thing, and oxygen carries mass. And so because the mass was reduced when oxygen left, the opposite of oxidation was reduction of the mass of that thing. Once it was understood that what was happening was electron transfer, that when something was oxidized, electrons were leaving it, and when something was reduced, electrons were being gained, The old names were kept and they were redefined according to the new understanding. Every redox reaction involves both processes. An electron leaves one molecule and is joined to another. And the electron leaves the molecule that is oxidized and it joins the molecule that is reduced. Okay, go back now to the dyes. Synthetic indigo could be reduced to indigo white. Methylene blue could be reduced to methylene white. The prefix leuco was also used, as in the reduction of Loth's violet to leuco-Loth's violet. Now, leuco means white, so this means white Loth's violet, which to me seems awkward. Leukocytes are white blood cells. They're called leukocytes because they are white blood cells. At some point, the simpler white terminology, methylene white, was largely lost in favor of the more awkward leucomethylene blue, which means white methylene blue. I will use this simpler and more elegant term, methylene white, in this episode. The redox reactivity is a common feature of the many dyes synthesized from aniline and its derivatives. And antimicrobial power is also broadly a feature of these dyes. Indeed, Ehrlich was never committed strictly to the methylene blue. In 1904, he developed a red dye named trypan red that he used to treat African sleeping sickness, and that also was derived from aniline. At the time of the Clark Review, methylene blue was used by chemists as a redox indicator that could test the propensity of a system to gain or lose electrons in the same way that litmus paper was used to test pH. Since living organisms have reducing power as a function of their ability to harvest electrons from their food, methylene blue could be used to test for the presence of microscopic organisms. You can't see them, but you can infer them because there's something in that stuff that is able to harvest electrons from food and reduce methylene blue to methylene white. For example, milk fresh from a cow would convert methylene blue to methylene white very slowly, while milk that had been bottled a while ago, meaning the bacteria in it had a chance to grow and multiply, would reduce methylene white very rapidly because the bacterial count was higher. The figure on the screen shows what's happening when methylene blue is reduced and oxidized. At the top, we see methylene white, also known as leucomethylene blue, or abbreviated MBH. The MB is for methylene blue, and if we abbreviate MB for methylene blue in general, then we can call the reduced form of methylene white MBH to signify the hydrogen, the extra hydrogen that's attached to it. And we can abbreviate the oxidized blue molecule, Mb+, to signify its positive charge. So what happens is that two electrons are incorporated into methylene blue to make methylene white. And when they are incorporated, there is a positive charge on the sulfur of methylene blue, or Mb+, that is neutralized by one of those electrons. The other electron is absorbed by the nitrogen, and that negative charge has to be balanced by a hydrogen. That's why the main differences when you look at the structures are that methylene white has a sulfur with no charge, and methylene blue has a sulfur with a positive charge, and its nitrogen has no hydrogen. There's also a change in the pattern of double bonds. In methylene blue, or Mb+, there is an extra double bond that is not present in methylene white. And if you're watching the video version, you can see that these double bonds that have changed are shown in blue and red to signify how they're changing. And what happens is double bonds are present in a relatively electron deficient state. And as you go from Mb+ to MBH, or from methylene blue to methylene white, you are adding electrons, and so you reduce the need for double bonds, and you see one double bond disappear and the other double bond migrate. The blue bottle experiment. At some later point, unknown chemists at Caltech invented an experiment called the blue bottle experiment, which found its way to the University of Wisconsin-Madison, where the college chemistry teacher J.A. Campbell picked it up in 1954. Campbell published it in 1963 as a tool to bring the teaching of the mechanisms and rates of chemical reactions forward from the 3rd and 4th year of college to as early as 7th grade. In this experiment, an unknown solution in a glass flask with a rubber stopper would appear colorless, but when shaken, it would turn blue within a few seconds. When allowed to sit for about 20 seconds, it would turn colorless again. This cycle could be repeated over and over again. Students would then manipulate the conditions in various ways to deduce what the nature of the mixture must be and how it works at various levels of details depending on how advanced those students were. The solution turns out to be a mixture of glucose, sodium hydroxide, and methylene blue. At rest, the dye is in the reduced state and therefore methylene white. Shaking the bottle mixes in oxygen from the air, which oxidizes the methylene white to form methylene blue. Allowing it to sit allows the glucose to reduce methylene blue back to methylene white. What happens in this experiment is as follows. The sodium hydroxide causes the glucose to ionize. And that's depicted in the figure by seeing carbon 5 of glucose with a negative charge. When glucose ionizes, that charge tends to migrate up to be shared between carbons 1 and 2. That's the formation of the glucosine dilate anion. This is reactive enough with Mb+ in order to be oxidized to generate NBH. And when it's oxidized, you wind up with a dicarbonyl form of the sugar that's called a glycosylose. Meanwhile, NBH has formed and needs to be reoxidized. So when you convert the glucosine dilate anion to the glycosylose dicarbonyl, and you convert methylene blue to methylene white, this is the 20 seconds that allows the bottle to lose its blue color. Now you shake the bottle. Oxygen comes in. Oxygen oxidizes the NBH to go back to Mb+. Every redox reaction has something oxidized and something reduced. What's reduced? Oxygen. What is it reduced to? Well, there are 2 electrons in NBH that are not in Mb+. If NBH reduces oxygen with 2 electrons, it makes the 2 electron reduced form of oxygen, which is hydrogen peroxide. Now, because this is an alkaline solution, everything that can donate a hydrogen ion wants to, because hydrogen ions are acidity that balance alkalinity. So the hydrogen peroxide ionizes to the hydroperoxide anion. Now, the dicarbonyl part of the glycosylose molecule is extremely reactive, and it can very easily be oxidized. So the hydrogen peroxide anion oxidizes the bond between carbon 1 and carbon 2 of the glycosylose to split the dicarbonyl apart. Carbon 1 becomes formic acid, which in an alkaline solution will lose its hydrogen ion and become the formate ion. And what's left is the 5-carbon sugar acid, arabinoic acid. This is a carboxylic acid version of a 5-carbon sugar. In this process, there's 1 hydrogen on carbon 1 that is not included in the formate molecule or in the arabinoate, and that neutralizes one of the hydroxide ions to become water. Okay, now you can rinse and repeat, right? So we let the blue color go away because the glucose-ene dialate anion reduced the Mb plus to MbH. It turned methylene blue to methylene white. Then we shook it up. Oxygen came in, oxidized the MbH to Mb plus, making hydrogen peroxide. The glycosylose and the hydrogen peroxide very much want to interact to become formate and arabinoate. And so our end products that are accumulating are formate and arabinoate. Our reactants that are disappearing is just glucose. The oxygen, every time you shake the bottle, the oxygen in the air is basically an infinite supply. And the methylene blue is never consumed. It just cycles over and over and over again. And so likely what makes this not an experiment that you could use the same batch for in perpetuity, eventually you do run out of the ability to do this, is that the glucose runs out. And so it can't reduce Mb plus anymore. And the ability for Mb plus and MbH to cycle is gone because the glucose is gone. But as long as there's oxygen coming in, and as long as there's glucose coming in, or there's glucose in reserve, the Mb plus MbH will cycle on and on and on and on. And that cycling will convert all of the oxygen that comes in to hydrogen peroxide, and eventually in the presence of this glycosylose to formate. So that's the blue bottle experiment. Now we need to talk about methylene blue radicals, photoexcited states, and demethylated metabolites. Methylene blue absorbs light between 550 and 700 nanometers in wavelength, which is mostly in the yellow, orange, and red parts of the spectrum, but includes a tiny portion of the green range. Absorption of light is the primary mechanism by which methylene blue radicals can be produced. Other free radicals may also be able to interact with methylene blue to create a methylene blue radical, but in the absence of light, these reactions appear to be very minor if they're relevant at all. Previously, we looked at the structure of methylene white, which we abbreviated MbH, and we looked at the structure of Mb plus, or methylene blue. And the methylene blue has a positive charge on the sulfur and no hydrogen on the nitrogen, reflecting 2 electron difference, 1 electron at the sulfur, 1 electron at the nitrogen. So to go from MbH to Mb plus or back and forth means the transfer of 2 electrons at a time. But if 1 electron is transferred to Mb plus, the positive charge on the sulfur will be eliminated. And we will show that this is a free radical because it contains an unpaired electron using a dot. And we will abbreviate it Mb dot. This is one of 2 possible methylene blue radicals that can be formed. And this is the semi-reduced methylene blue radical, Mb dot. Call it semi-reduced because it has been reduced with 1 electron, but not 2. 2 electrons would generate methylene white, but reduction with 1 electron generates the semi-reduced methylene radical, abbreviated Mb dot. Now, methylene blue can also be oxidized. So if you start with the methylene blue structure and you cannot lose any more electrons on the sulfur or on the nitrogen because they're both in their oxidized form, you can take an electron from the nitrogen, and taking an electron away generates a positive charge on the nitrogen and makes the nitrogen a free radical. So now we have a positive charge on the sulfur and a positive charge on the nitrogen, and that's 2 positive charges, and we also have a free radical. This has not been semi-reduced, it's been oxidized by 1 electron. And so the oxidized methylene blue radical is symbolized Mb dot 2 plus. Now we have 2 possible methylene blue radicals. We have Mb dot and we have Mb dot 2 plus. Mb dot is the semi-reduced methylene blue radical. Mb dot 2 plus is the oxidized methylene blue radical. Free radicals are far more reactive than things that are not free radicals because electrons have a voracious appetite to exist in pairs. So these guys will react with something. Now, generally the way these form is from the effect of light. So because methylene blue absorbs light in the wavelengths that I had just given you, the light can excite the methylene blue. And when we excite methylene blue, we symbolize this with an asterisk. So the absorption of light makes methylene blue, or Mb plus, go to Nb plus asterisk. Further, on the Nb plus asterisk, the excited methylene blue, we are going to add a superscripted number to the beginning, either a 1 or a 3, depending on whether it is a singlet or a triplet. Now, what this means is most molecules, and oxygen is an exception, but the rule is that most molecules have their electrons existing in pairs that are angled with their momentum of movement angled opposite one another. And this is called the singlet state. Oxygen at rest actually has its electron pairs in this same angle, and that's called the triplet state. And oddly enough, for details that are beyond the scope of this actually contributes to the fact that oxygen, paradoxically, is an extremely strong oxidizing agent, yet is highly stable in the air. It's not oxidizing everything that could possibly be oxidized, not by any stretch of the imagination. It's actually very hard to get oxygen to start reacting with something. To start a fire, you can do it, but you generally have to put some movement into oxygen. Okay. So most molecules are the opposite. When they're at rest, they're in the singlet state. Exciting them has the possibility of putting them into the triplet state. Remember, the electrons angled opposite one another are the singlet state. When you add energy, you allow something to exist in a less probable state. Imagine, take an airplane, right? It takes a lot of fuel to get human beings into the wildly improbable position of being way up in the air, right? So similarly, it takes energy to get electrons that at rest want to be angled opposite one another to flip to being angled together so that their angular momentums are acting in an additive rather than in a antagonistic or canceling out fashion. So when methylene blue gets excited by the absorption of light, there are several possible outcomes of that. So one is for it just to go back to where it came from by fluorescing. So some different wavelength of light can leave. Methylene blue has some capacity for fluorescence, but it's very, very low compared to things that we think of as fluorescent molecules. Another possibility is it comes back down from where it went, back to where it came from, simply by translating that energy to something else. So it could come down and release the energy as kinetic energy that could go into heat. Alternatively, that energy could flip those electrons into the triplet state. When we have methylene blue go from the excited singlet state to the excited triplet state, it goes from Nb plus asterisk superscript 1 to Nb plus asterisk superscript 3. That's quite a mouthful. So verbally, I'm just going to call these singlet Nb and triplet Nb. Now, the triplet Nb is a wildly improbable state that wants to get back to, the airplane. It runs out of fuel. What happens? Right? The more improbable of the state that you get because of the energy input, the more that thing is ready to go back to the probable state. So when you have something get to the wildly improbable triplet Nb state because of the input of light energy, it wants to find a way back. Right? Excited can be fun sometimes, but at some point you need to calm down. Okay, so there are two routes to get back to normal for the triplet Nb. One is to react with triplet oxygen, the normal oxygen, to make singlet oxygen, which is extremely reactive. Now, the second path that the Nb can take to try to relieve the extra energy that it has is to oxidize Nb plus, that is not excited, just other NB plus in the solution, to generate two other improbable but less improbable states between it and the other NB plus molecule that it's oxidized. So if triplet NB oxidizes an NB plus in the solution, the NB plus in the solution will become the oxidized radical, NB.2 plus. If the triplet NB took a single electron from NB plus to make the oxidized radical, NB.2 plus, then it has gained a single electron, and it is now the semi-reduced methylene blue radical NB dot. Now, NB.2 plus is actually relatively stable. It's improbable to get to, but once you get there, it can stay in the solution for quite a while. By contrast, NB dot is extremely unstable, and it wants to get back to the ground state, in this context, back to NB plus as quickly as it can. And it does that by taking this electron that it now has, extra electron, and giving it to oxygen. One electron transfer to oxygen makes superoxide. O2 goes to O2 dot minus, or minus dot. This is the production of the superoxide anion. And now NB can get back to the unexcited, plain old methylene blue NB plus state. But in this process, we have created singlet oxygen, superoxide, oxidized methylene blue radical, and semi-reduced methylene blue radical. And these collectively, especially the singlet oxygen, superoxide, and semi-reduced methylene blue radical, or NB dot, are collectively cytotoxic. They're extremely powerful oxidants, and this explains the photoinactivation of all kinds of pathogens, including bacteria, viruses, and fungi, and the destruction of tumors through methylene blue catalyzed phototherapy. Now, if we go back to the structure of plain old methylene blue, you'll see it depicted with two nitrogens on the sides. And these sometimes are shown with two methyl groups each, or sometimes they are just shown with lines attached to them, as I shown in the video. And regardless of how it's shown, those are methyl groups. So on the left side of methylene blue and on the right side of methylene blue, you have two methyl groups each. That's 4 total methyl groups. And as you lose the methyl groups, you'll lose them progressively on one side and then the other. And as you lose 1, 2, 3, 4 methyl groups, you wind up getting azure B, then azure A, then azure C. And then finally, when you lose all 4 methyl groups, what do you get? You get Loth's violet, or thionine, which explains, going back in history, how Caro was trying to invent a high-yield form of Loth's violet and stumbled his way into making methylene blue, because methylene blue is nothing but Loth's violet with 4 extra methyl groups. Now, azure A, B, and C are common contaminants of methylene blue, but rat experiments suggest that mammals can demethylate methylene blue, because when you look in the rat's urine after you administer methylene blue, you see more of the demethylated metabolites than could be explained from the contamination in the first place. That does not mean that this molecule is a methyl donor, because demethylases do not necessarily take off methyl groups. They take off that one single carbon. A methyl group is CH3, a carbon with 3 hydrogens. That carbon might wind up as a carbonyl group or as carbon dioxide, etc. So we don't know exactly how methylene blue is demethylated, and there's no evidence that it's a methyl donor. Now, there is evidence that azure B acts like methylene blue, but more powerfully, which could allow you to frame methylene blue as a prodrug for azure B. Arnheiner Schirmer of the University of Heidelberg took 30 and 120 milligrams of Azure B himself on separate occasions. He weighed 60 kilograms, so these doses were 0.5 and 2 milligrams per kilogram. He reported that it was similar to taking methylene blue. Immediate discoloration of mucous membranes and teeth, a bitter taste that was, quote, burning but not unpleasant for an adult. Then green and later blue urine, reaching maximal coloration at 12 hours, and the high dose but not the low dose, so 2 milligrams per kilogram body weight for him, 120 milligrams but not 30 milligrams, produced the, quote, tonic invigorating effect expected of methylene blue. In addition to these metabolites, methylene blue can form dimers, so two of them can bind together. It can also form polymers, but you're generally only going to see the polymers in engineering projects like using methylene blue to make solar cell batteries. And generally, when methylene blue is administered, it's going to be present as monomers, meaning a single molecule in solution, except at very high doses. For example, if you inject a tumor with a high concentration, you will definitely see some dimers, because as the concentration rises, the higher it gets, the more you form those dimers. And then final comments on other forms of methylene blue is that in the presence of oxygen and a semiconductor, light can degrade methylene blue to carbon dioxide, water, nitric acid, and sulfuric acid. There's a lot of interest in how to degrade methylene blue in order to get rid of the color and because it is seen as an environmental pollutant. All right, now what does methylene blue do in the human body in the context of complex physiology? Well, it acts as a redox agent in the same way that it acts as a dye or in the blue bottle experiment. But the things that it can oxidize and reduce are very many. Everything that is capable of a redox reaction exists as a redox couple. And what that means is that the oxidized form and the reduced form can be thought of as two sides of a coin. So NBH and NB+, the two electron differing main forms of methylene blue and methylene white, are a redox couple. For every given redox couple, there's three principal things to think about. First, each redox couple has an intrinsic affinity for electrons. If the couple has a high affinity for electrons, it will tend to oxidize, it will tend to take them. If it has a low affinity for electrons, it will tend to reduce, it will tend to lose them. Second, each couple has a range of conditional propensities to take or give electrons based on their relative concentrations. For example, if NBH rises way above the level of NB+, NBH will tend to do the reducing until they fall into an equilibrium. If NB+ raises to much higher concentrations than NBH, NB+ will tend to do the oxidizing until they fall into an equilibrium. Third, some reactions, they just happen fast and others just happen slow. And there's little regard to whether they would predominate over other reactions given an infinite amount of time. This is just driven by deep details of physical and organic chemistry that differ for every single possible reaction. Now, as an example, in the blue bottle experiment, oxygen takes only a few seconds to oxidize all the NBH, turning the solution blue. The fact that the oxygen is in net breaking down the glucose to arabinoic acid and formate shows that oxygen very much wants to oxidize the glucose and is strong enough to do so, and yet the rate at which this happens is meaningless in the absence of methylene blue. This is why if you open a bottle of fruit juice, you don't within seconds, nor within minutes or days or weeks even, but you don't in 3 seconds have a toxic level of formic acid in the fruit juice. Because even though the oxygen is strong enough to break the sugars into formic acid, and even though that's a reaction that can happen, the rate at which it will do that without something to catalyze it is meaninglessly slow. So methylene blue is catalyzing that reaction in the blue bottle experiment by making it happen, by making oxygen convert to hydrogen peroxide much more rapidly than it would without a catalyst. And catalysts then, and the main catalysts in the human body are enzymes, which are regulated with very complex physiology. But catalysts in general are able to control what happens because they control how fast things happen. If you make something happen much faster than the alternative, you are making it happen instead of the alternative because the thing that could have gone into the alternative gets used up doing what you are catalyzing. Right? So catalysts, by controlling the speed of things, also control what happens. And generally, the catalysts in the human body are enzymatically controlled, and the enzymes are controlled by complex physiology that has been developed over the course of a much longer time than since 1876. Methylene blue is a catalyst that does whatever it does without regard to your physiology. Now the question will be, what exactly is that? Okay, so if we rule out the things that could happen but are too slow to consider, we basically have three possible things that methylene blue could do. So first of all, the possibility one is it has a higher affinity for electrons than another substance. It will oxidize that target. Possibility two is that it has a lower affinity for electrons and it will reduce that target. And then possibility three is that it has a similar affinity for electrons as the other substance. And if it reacts with it fast enough to be relevant, what will happen is that it will cause redox cycling of that target. Now, I made this diagram to summarize the research that we are going to talk about momentarily. This shows MBH being oxidized to MB+, and MB+ being reduced to MBH. As MBH is oxidized, it will tend to reduce the target. As MB+ is reduced, it will oxidize the target. So, what this implies is that methylene blue can take electrons away from NADPH or NADH, both forms of niacin or vitamin B3, or take them away from enzymes that use FADH2. And these enzymes could be glutathione reductase, they could be thioredoxin reductase, they could be succinate dehydrogenase, also known as complex 2 of the respiratory chain in the mitochondria, or alpha-glycerophosphate dehydrogenase, which is an enzyme that is involved in glucose metabolism. And it can also take those electrons from iron in the reduced state, which is Fe2+, or it can take those electrons from complex 1 of the respiratory chain. And in the process of any of those things, it becomes methylene white. Now, methylene white can donate electrons or can reduce cytochrome C of the respiratory chain. Although not shown in the diagram, I'll argue later that can also reduce complex 4 of the respiratory chain. It can reduce oxygen to hydrogen peroxide in vivo, like it does in the blue bottle experiment. It can reduce oxidized iron to reduced iron. It can make Fe3+ go to Fe2+, and it can reduce the riboflavin or FAD that is bound to the monoamine oxidase A enzyme and is needed to oxidize monoamines and clear them, such as neurotransmitters, mainly neurotransmitters, and that is how it inhibits that enzyme. In addition, there are conflicting reports about whether MB+ does or does not directly oxidize glutathione. My best effort to synthesize these two papers is to say that MB+ does directly oxidize glutathione, but because in the presence of sufficient reducing agents, as would happen in human cells, it happens too slowly to be relevant. And so that's why I didn't put it on the diagram. Further, some authors, and we're going to talk about this more later, have argued that MBH reduces hydrogen peroxide to water. However, if this is possible, it is very unlikely to net happen in vivo because the presence of methylene blue makes hydrogen peroxide last for 2.5 times as long as it would otherwise. And that's shown in isolated mitochondria from the brains of guinea pigs. So the conversion of H2O2 to water is not shown on the diagram because I don't think that is a meaningful in vivo reaction, but we'll talk about it more later. Methylene blue can rewire the mitochondrial respiratory chain. One of the most important potential uses of methylene blue is to rewire the mitochondrial respiratory chain, which is the means by which we use oxygen to derive energy from our food in the form of ATP. We can think of the respiratory chain as step 2 in a 2-step process of energy metabolism. In step 1, we break apart the chemical bonds in fat, protein, and carbohydrate, releasing the carbons as carbon dioxide into the breath, loading the high-energy electrons on special carriers such as NADH, a form of niacin, and FADH2, a form of riboflavin. In step 2, we take the energy from the electrons and we use it to make ATP. Oxygen enables this process by securing those electrons to itself in its own conversion to water. Once the electrons are part of the water molecule, they're in a much lower energy state than they had been when they were first loaded onto NADH and FADH2. Securing the electrons in this lower energy state allows the remainder of the energy that they had contained to be harvested for ATP production. Step 1 includes glycolysis, beta oxidation of fatty acids, amino acid oxidation, and the citric acid cycle. Step 2 is the mitochondrial respiratory chain. The mitochondrial respiratory chain is shown in this diagram, and there are 2 primary routes that electrons can take through it. The main route is the one shown on the top, mediated by NADH, and the secondary route is the one shown on the bottom, mediated by FADH2. And the reason that the top route is primary is because most of what we eat winds up producing NADH rather than FADH2. Now, you can modify the ratio. For example, fatty acids and leucine have the highest yield of FADH2, whereas carbohydrates have the highest yield of NADH. Intermediate between those 2 extremes is certain other amino acids, such as the other branched chain amino acids, isoleucine and valine, as well as the amino acid lysine. But even in the case of fatty acids and leucine, they're generating 2 times as much NADH as they are generating FADH2. And so therefore, generally speaking, the first route that feeds into complex 1 shown on the top is the one that predominates. Now, complex 1 does not feed into complex 2. They are alternatives. So complex 1 feeds into coenzyme Q10, which is shown here as Q, and then into complex 3, then to cytochrome C, and then to complex 4, also called cytochrome oxidase. Complex 4 is where oxygen is converted to water. Complex 5 is ATP synthase, and this is where the energy from the food is translated into the chemical bond energy in ATP. The alternate route is for succinate being converted to fumarate, which is what's shown here, but generally speaking, for anything that donates FADH2 into the respiratory chain, and there are some alternatives besides succinate coming from the citric acid cycle, that will go to, the electrons will skip over complex 1, they'll go into complex 2, and then from there, they'll go to coenzyme Q10, and then they will share this. That's where the 2 routes converge. So once you're at coenzyme Q10, you're doing the same thing no matter where the electrons came from. They're going to complex 3 next, they're going to cytochrome C after that, and then they're going to complex 4, where oxygen is converted to water. Now, 3 of the first 4 complexes, that is complexes 1, 3, and 4, are hydrogen ion pumps. And what they're doing is they're taking food energy and they're using it to translate it into the kinetic energy of pumping the hydrogen ions across the membrane. And those hydrogen ions have potential energy by virtue of their position. They want to spread out. And if they're all pumped to one side of the membrane, they all want to come back. And that desire to come back is very similar to a hydroelectric dam, where you have water that's trying to rush down, the dam stops it. There's energy, there's potential energy of position in the water being stopped that really wants to use gravity and continue through. And if you open that water up to a channel, it will get pumped into where you want it to go. and it'll spin a turbine that then is turned into electrical energy. So very similarly, what's happening here, the hydrogen ions are like the water in the hydroelectric dam. And by virtue of their position, they want to come back inside the matrix of the mitochondria, and they are funneled through complex 5, also known as ATP synthase, where the kinetic energy of their movement spins a rotor at 8,000 RPM that is matched torque for size 60 times more powerful than a diesel engine. And that kinetic energy then is translated into the chemical bond energy of the ATP molecule, much in the way that the kinetic energy of the water in a hydropower plant is translated into electrical energy. What's enabling this is the oxygen that is converted into water in complex 4. But what's driving it is actually the demand for energy. So this is all driven by a pull forward mechanism of ADP. So if you are overfed and underexercised, you'll have a lot of ATP, but you won't have a lot of ADP. When you have been fasting and you're using ATP, or when you exercise and you're using ATP, it gets converted to ADP. That is the need to make this thing run. And this pull forward mechanism mediated by ADP is what makes everything flow. Now, generally at complex 1, we have a small number of electrons that are actually used to produce superoxide from oxygen. And this is at a rate of about 1 to 2% of the oxygen that is incorporated in some way into the mitochondrial respiratory chain. So 98 to 99% at complex 4 goes to water, but 1 to 2% at complex 1 goes to superoxide. And superoxide, due to spontaneous reactions and enzymatic reactions, is very, very quickly, especially by the manganese-dependent enzyme mitochondrial superoxide dismutase, converted to hydrogen peroxide. So through superoxide, this winds up being H2O2, or hydrogen peroxide, that can then act as a signaling molecule. So generally, the amount of superoxide and thus hydrogen peroxide produced by the mitochondrial respiratory chain is a signal of the tone of the supply of energy versus the demand. If you have too much incoming energy and not enough demand for it, superoxide and therefore hydrogen peroxide increases, and that will shut down the incoming energy. And this plays a role in hyperglycemia, for example. If, why is obesity tied to hyperglycemia? One of the mechanisms is that in the overfed and underexercised state, too much incoming energy, not enough utilization of energy at complex 1 generates more superoxide and less hydrogen peroxide, which then inhibits glucose uptake. Now, it doesn't always work like that. So some people would say you want fat and leucine to feed complex 2, so you can skip over complex 1 and avoid this condition of energy supply-demand mismatch. But not really, because if you don't have enough ADP, the electron transport chain is backed up from the end. And if you feed complex 2 with fat and leucine, and that energy cannot go through to the end because ADP is not present, what happens is it just gets backed up and you get reverse electron transport into complex 1, you generate superoxide. Right? So there's no hack of eating fat and leucine to get around being overfed and underexercised. Now, we will talk about fat and leucine as a hack to get around a complex 1 disorder, but being overfed and underexercised is not a complex 1 disorder. It is being overfed and underexercised. You cannot hack your way around that, because if you try, all you'll get is reverse electron transport, more superoxide, more H2O2, more result of being overfed and underexercised. Now, these complexes have way more detail than suggested in the diagram. Altogether, it requires at least 297 genes in order to make this chain assemble. there are over 60 independent proteins that make up the complexes. And the electrons don't just go from one complex to the next complex. Within the complex, they go through many electron transferring sites that are made of a riboflavin molecule in the form of flavin mononucleotide, or FMN, 12 iron sulfur clusters, a CoQ10, 6 iron-containing hemes, and 3 copper atoms before they ever get to oxygen. Now, there's a reason for all this complexity. If all the energy of a food molecule is released at once, we wouldn't be able to harness it efficiently, and we would lose it as heat. Similarly, if you combust all the fuel in your car engine, you don't get from point A to B, your car explodes. If you want to get from point A to point B, you have to use the gas pedal through the way that in the mechanism that the car is designed to burn very small amounts of fuel at a time continuously until you get where you need to go. Yet sometimes part of the engine can be broken. For example, there are 297 independent genetic defects, not mutations, independent genetic defects in the respiratory chain, and there are toxins and nutrient deficiencies that can disrupt parts of it. However, the only nutrients that are used in one of the complexes but not the others are riboflavin in complex 1, copper in complex 4. Riboflavin is not specific to complex 1 in the sense that riboflavin is used all over step 1 of energy metabolism, but copper is very specific to complex 4 in the sense that copper is used indirectly for energy metabolism by iron handling or neurotransmitter balance that can regulate energy metabolism, but it's not directly used in energy metabolism anywhere except complex 4. So copper is very specific to complex 4. Now, copper is not the only nutrient in complex 4. For example, iron is also there, but complex 4 is the one place in energy metabolism where copper shows up directly. CoQ10 is not an essential nutrient, but it is found in food, especially heart meat. And CoQ10 can become conditionally essential if someone is not making enough, either because of a genetic defect or because of poor nutrition leading into CoQ10 synthesis. So altogether, it's riboflavin, copper, and CoQ10 that stand out as being nutrient deficiencies that might disproportionately hurt one complex versus another. And as we'll see, this is the real thing to understand when you're talking about mitochondrial dysfunction. You're talking about what is the specific impairment and what can we do about it? Because the things you would do about the different blocks are different. So yes, there are things that you can generally do that are generally good for mitochondrial health, like eat well and exercise and sleep, etc. But when we get down to the nitty-gritty details, we really want to understand what is the complex that's hurt, because the implications for what you want to do about it are different. Now, the possibility that you could have a specific impairment also offers a second benefit of all the complexity, because that means that if one part is hurt, the other parts can step up their game to compensate. And that can require some rewiring, such as increased use of fat and leucine to feed complex 2 if complex 1 is blocked, or increased use of carbohydrate for fuel if complex 2 is blocked. The ability of methylene blue to rewire the respiratory chain has mainly been studied in the context of inhibitors. And I'm going to show you my models that I've synthesized from the literature on those inhibitors. If complex 1 is blocked, NADH cannot be oxidized at complex 1. That has 2 implications. One is that the NADH cannot feed the electrons into the chain to make ATP. But a second problem is that you don't have enough NAD plus to run the rest of energy metabolism, like the citric acid cycle, glycolysis, beta oxidation, and so on. And when complex 1 is blocked, for example, with the specific inhibitor rhodinone, which is a natural flavonoid that some indigenous groups used to poison fish so that the fish would develop an acute respiratory chain disorder, they would come up to the surface to gulp for air, and then that would make them easier to kill. And it's been used in the United States since 1952 and in several other countries since the 1980s in order to kill fish in the water supplies. And in animals, it's used to induce a model of Parkinson's. Parkinson's has some evidence for being a form of a complex 1 disorder because the genes associated with Parkinson's impair complex 1. And so you can speculate that maybe swimming in American waters or eating the fish here might contribute to Parkinson's, perhaps. In any case, if you block complex 1 with Rotenome, what you can show experimentally is that when you put methylene blue into the system, methylene blue will take the electrons from NADH and it will deliver them to somewhere in the chain that winds up reducing cytochrome C. So we can't say exactly where that is, but it's somewhere after the CoQ10 oxidizing site of complex 3, but early enough that the electrons wind up on cytochrome C. Now, because each complex has many sites where electrons can get funneled into, or at least several sites, we don't know exactly where it's going. So on the one hand, you are skipping over the hydrogen ion pumping of complex 1, and we don't really know whether you're skipping over the hydrogen ion pumping of complex 3. So we're losing the hydrogen ion pumping of at least one, if not two, of the three pump complexes, and because the hydrogen ions are what drives ATP synthesis, that means that we're losing somewhere between 33% and 67% of the ATP that could have been gained by that NADH. So this is not ideal. This is not better than the way it usually works, but it's better than a complex 1 disorder, because in a complex 1 disorder without the methylene blue, you would just be straight up locked at complex 1. The NADH could not go anywhere. The NADH would accumulate. Lactate would accumulate as a result to try to rescue glycolysis. Your glycolysis would shut down, your beta oxidation would shut down, your citric acid cycle would shut down as a result of the inability to oxidize the NADH, and you'd feed nothing into the electron transport chain instead of 1/3 to 2/3 of the ATP that you're getting, right? So you're changing two things. You are allowing 1/3 to 2/3 of the ATP to be made from the NADH, and you're allowing the NADH to be converted to NAD plus to go back to run glycolysis in the citric acid cycle, and glycolysis generates 2 ATP per run. Citric acid cycle generates 1 ATP per run. So you're rescuing part of the ATP from the respiratory chain, and you're also preventing the ATP from glycolysis in the citric acid cycle from being shut down. Now, if you block the coenzyme Q10 oxidizing site of complex 3 with antimycin, which is a toxin made by strep bacteria, you basically get the same exact rewiring. And this is why I say that MBH has to be delivering electrons after the coenzyme Q10 oxidizing site of complex 3. It's just what we're showing in these is that cytochrome C is getting reduced. That's what's being shown experimentally. Okay, now, if we go to complex 2, we start to get into more ambiguous territory where there's more controversy in the literature. What I'm showing you on the screen is my model synthesized from 2 different papers. One of them showed that if you feed complex 2 with substrates that feed FADH2 into the complex, such as succinate or alpha-glycerophosphate are the 2 fuels that would be used in this context. If you feed it into complex 2 and you block the complex 3 oxidizing site with antimycin, you cannot get cytochrome C reduced. Okay, so that paper concludes that methylene blue cannot rescue complex 2 because it cannot move electrons from FADH2 to cytochrome C. Now, on the other hand, the other paper that I considered to make this diagram showed that you can use methylene blue in this context to rescue 2 things: the oxygen consumption of the mitochondria and the H plus or hydrogen ion gradient around the membrane. So that means that you are getting hydrogen ion pumping and you are getting oxygen consumption. And if you're not getting cytochrome C reduction. That means that you're delivering the electrons after complex 3, but if you're not reducing cytochrome C, it's got to be being delivered to complex 4. Now, I don't think either of these papers reached the appropriate conclusions, because the paper that showed you rescue oxygen consumption and the hydrogen ion gradient did not look at cytochrome C reduction. And the paper that showed you cannot rescue cytochrome C reduction did not look at oxygen consumption and the hydrogen ion gradient. If you synthesize them together, then you see a better picture emerge, where complex 4 delivery is the only option that makes any sense. Now, the paper that showed you rescue the hydrogen ion gradient showed that if you poison complex 4 with cyanide, you abolish that. And so they concluded, I believe erroneously, that methylene blue cannot deliver electrons to complex 4. Why do I show it delivering it there in my diagram? Because what cyanide does is it occupies the oxygen binding site of complex 4. If you look at the complex 4 structure, the oxygen binding site is a heme iron atom, or a heme molecule containing an iron atom and a copper ion that secure the oxygen like this. Okay, before you get there, electrons flow through 4 sites with 2 heme iron atoms and 2 copper ions. That means that there are sites prior to the oxygen binding site poisoned by cyanide that methylene blue could deliver the electrons. So if we synthesize these findings, we know the electrons do not go to cytochrome C. They cannot get to complex 4 if oxygen is not there. But that doesn't mean that they can't get to complex 4. That just means that complex 4 shuts down if oxygen's not there, because there's nothing drawing the electrons through, right? So if oxygen is present, then they must be going to the sites proximal to the oxygen binding site, to a heme iron atom or a copper ion prior to the oxygen binding site, and finding their way in to reduce oxygen to water. That's the only way that you can synthesize all these findings together. So my model is, if complex 2 is blocked, methylene blue oxidizes FADH2 to make FAD. This allows FAD to go run citric acid cycle. Now the NB plus becomes NBH, and it skips over complex 3 and goes to complex 4. It would appear that you are getting the hydrogen pumping activity of complex 4, at least part of it, and you are not getting the hydrogen ion pumping of complex 3. So you're losing half of the ATP production that should come from the FADH2. But you are preventing the citric acid cycle from getting shut down for lack of FAD, and this is better than the alternative with no methylene blue in the case of a block at complex 2, because you've rescued a portion of the ATP that could have been produced. A complex 2 block should not be as bad as a complex 1 block, because remember, most of your energy is funneled through complex 1, not complex 2. So there's no reason with a complex 2 specific block that complex 1 is not operating, delivering to complex 3, etc. So your ATP decrement is not that bad. And that would especially be true if you treated the complex 2 disorder with a high carbohydrate, low fat, minimally adequate protein diet, where you are purposefully shifting energy into NADH to go through the working complex 1. But methylene blue can come and rescue the complex 2. Now, part of the reason that I show that it's feeding into complex 4 and that's allowing oxygen to be consumed at complex 4 is because the data that came from this paper, and I want to focus specifically on succinate with and without methylene blue, and on alpha-glycerophosphate with and without methylene blue. So one model for saying why oxygen consumption could be increased would be to say, well, the methylene blue is just converting the oxygen to hydrogen peroxide. That would not explain why the hydrogen ion gradient was rescued, but it would explain why the oxygen consumption was increased. If you look at these numbers, what you'll find is that when you add methylene blue to succinate, you get an increase 1440 over 1094. When you add it to alpha glycerophosphate, you get an increase 550 from 335. These are the same concentrations of methylene blue. And if you calculate these numbers out, what you'll find is that the increased oxygen consumption is much better explained as a function of the basal oxygen consumption with that fuel than it is by the concentration of methylene blue. In other words, if a given concentration of succinate produced basically 3 times as much oxygen consumption as the amount that they used of alpha glycerophosphate. And the increase with methylene blue is also about 3 times the increase that you get when you add in methylene blue to alpha glycerophosphate. What that means is that methylene blue is not bringing oxygen there because methylene blue is there. It's bringing oxygen there because the fuel that you've put into the respiratory chain needs to be oxidized, right? So if we come back here, methylene blue it's only stimulating as much oxygen uptake as is needed to oxidize the fuel that is present. And in this context, it makes much more sense that the methylene blue is primarily feeding electrons into complex 4 and allowing the oxygen to be reduced to water there in this context. Now, I'm going to show you another context where things get different. Okay. You can block complex 4 with cyanide, hydrogen sulfide, or sodium azide. And if you block complex 4, the model that I'm showing here is also a little bit more deserving of controversy. What they're doing is they're mixing in vivo evidence with in vitro evidence to try to explain what could have happened. Okay, so what they did show in vivo is that you can dramatically rescue sheep or rats from lethal doses of hydrogen sulfide in sheep or lethal doses of cyanide in rats. And this is associated with decreased lactate, which you would expect if you oxidized NADH to NAD+. That's what we know in vivo. Okay, so then what they did is they reasoned through it. They said, how could this be possible if all of the earlier explanations that I just gave you and that are known in the literature are things such as NBH will deliver electrons to cytochrome C, or in what I'm arguing, proximal to the oxygen binding site of complex 4. If you block the oxygen binding site of complex 4, none of those explanations make any sense of why you make the sheep and the rats live, even though you gave them lethal doses of hydrogen sulfide or cyanide. So what must be happening? What they hypothesized was that in this case, the NBH will do the reducing of oxygen directly. Not because that's what usually happens, but because when the more favorable condition of the oxygen being converted to water at complex 4 is not possible, and the oxygen is not even in the complex 4 sites trying to get there and it can't, you have the NBH loose, you have the oxygen loose, and you have a need to get fuel oxidized. So what happens? The NBH reacts with the oxygen, makes hydrogen peroxide. The hydrogen peroxide crosses the membrane, goes to the cytochrome C on the other side of the membrane, and oxidizes it. That makes the oxygen ultimately become water. In this process, you have a dual rewiring, where one route of electrons is to go from NADH to Mb+, making it MBH, to go from MBH to oxygen, to make it hydrogen peroxide, to make the hydrogen peroxide oxidize the cytochrome C and become water. Now, if you only did that, you'd run out of reduced cytochrome C. So the other route is the normal route up to cytochrome C. NADH delivers electrons to complex 1, they go to coenzyme Q10, they go to complex 3, then they get to cytochrome C. that's blocked by the cyanide or the hydrogen sulfide or the sodium azide because the cytochrome C cannot deliver electrons to complex 4 if there's no demand for them by oxygen. And so now those electrons wind up being added to hydrogen peroxide to make water. So that means that half of your ATP is lost when it goes from NADH through methylene blue to oxygen to make hydrogen peroxide. But doing that is what is allowing you to take the other half, run them through complex 1, coenzyme Q10, complex 3 to cytochrome C, and keep that running. Right? So 2 electrons, you have a water molecule, an oxygen molecule. To go from oxygen to hydrogen to water requires 4 electrons. Okay, 2 of them went from NADH to methylene blue to make hydrogen peroxide. 2 of them went from NADH to coenzyme Q10 to complex 3 to cytochrome C, and then got added to the hydrogen peroxide to make water. Now, their evidence for this is in vitro evidence showing that hydrogen peroxide can oxidize cytochrome C. And you can get electrons to flow that way in vitro. So it's plausible that this is what's happening. And it's the only sensible explanation for why you get rescuing of lethal cyanide and hydrogen sulfide toxicity, and why it's associated with decreased lactate, because now you're oxidizing the NADH. The NAD plus can go back to glycolysis and run glycolysis without lactate production as a result of this. Okay, now the final block, and this is only known experimentally, so you can use oligomycin, another strep toxin. Well, I guess if you got a strep throat, you probably have this happening in your throat, but generally speaking, as systemically, this is only happening experimentally. Oligomycin, a strep toxin, is used to poison complex 5 or ATP synthase. In this case, you have a terrible situation that is made somewhat more handleable. Because you've shut down ATP synthesis in the respiratory chain, you shut down the whole respiratory chain because the whole thing is useless. But what can you do? You can get Mb plus to oxidize NADH, to then become MBH to oxidize oxygen, to reduce oxygen to hydrogen peroxide. So you just have complete conversion of oxygen to hydrogen peroxide and no ATP production in the mitochondria at all. But what has methylene blue allowed you to do? It's allowed you to oxidize NADH to NAD+. That can go to the citric acid cycle, make 1 ATP per turn. It can go to glycolysis, make 2 ATP per turn. So if you imagine oxidizing a glucose molecule, you would get 2 ATP in glycolysis, and then you get 2 acetyl-CoA that generate 2 turns of the citric acid cycle, generating 2 more ATP. So you get 4 ATP instead of 30 to 32 ATP for the full oxidation of glucose. So it's not a good situation, but that's better than dying of cyanide toxicity and hydrogen sulfide poisoning. Now, in each one of these situations, we have shown how methylene blue will give you a respiratory chain that works better than the defect that was present, but always operates at a loss of ATP from baseline. And so what has been shown in the oligomycin paper is that if you have no inhibitors, methylene blue causes a decrease in ATP synthesis that is just as strong as the increase that it causes in the presence of inhibitors. So what does that mean? If you don't need methylene blue to rewire the respiratory chain, rewiring the respiratory chain causes an obligate loss of ATP because all of the rewirings that I've shown you operate you're losing some of the complexes when you skip over them, right? The complexity is there for maximal extraction of energy. Lose some of the complexity with a short circuit, you lose ATP. So methylene blue rescues a defect in the mitochondrial respiratory chain through the rewiring, but it doesn't make the chain better. So that means you're just, from a basic engineering standpoint, you have to see that it's not possible for methylene blue to act as a general enhancer of mitochondrial health, it is only possible for it to fix specific defects, because there is no rewiring of the respiratory chain that can make it better than the one that it is designed, than the wiring that is designed into it, right? So regardless of whether you're thinking about this from the standpoint of creationism or Darwinian evolution or intelligent design or systems biology or engineering, there's no way on earth that a dye that was designed to make a blue color that wouldn't come out in the wash can somehow make the respiratory chain that has up to, close to 300 genes driving the assembly of 60 proteins into a complex with 12 iron sulfur clusters, a riboflavin, a CoQ10, 6 hemes, and 3 copper atoms, making basically close to 24 transporting sites to turn a rotor in a microscopic machine at 8,000 RPM that's 60 times more powerful than a diesel engine. There's no way some guy in 1876 made a blue dye that doesn't come out in the wash that is somehow able to make that better than it should be in a healthy person. Methylene blue increases hydrogen peroxide. We knew that methylene blue increased hydrogen peroxide in vitro from the blue bottle experiment. In some of these models of rewiring the respiratory chain, methylene blue is supposed to generate hydrogen peroxide in 2 of the models. Now, the cyanide, hydrogen sulfide, and oligomycin papers were published by Philippe Haouzi's group at the Penn State College of Medicine. And in the oligomycin paper, they argue that the final product of methylene blue's reduction of oxygen to water, reduction of oxygen is water rather than hydrogen peroxide. That is, NBH would first reduce oxygen to hydrogen peroxide, but then NBH would again reduce the hydrogen peroxide itself to water. Now, they didn't base that on hydrogen peroxide measurements, but rather on the relative rates of oxygen consumption versus methylene blue reduction. And this is based on basic math, okay? So 2 electrons convert oxygen to hydrogen peroxide. 2 electrons convert hydrogen peroxide to water. That means 4 electrons are needed to go from oxygen to water. To go from methylene blue to methylene white requires 2 electrons. So for methylene blue to take 2 electrons from NADH or NADPH or FADH2 or what have you, and donate them to oxygen once would generate hydrogen peroxide. You would have to get a second reduction of methylene blue to methylene white for a second reduction of hydrogen peroxide to water. So what they said was, if the rate that methylene blue is reduced to methylene white is consistent with 4 electrons coming in for each oxygen molecule that gets pulled in, then we're getting water as the final product. But if it's consistent with 2 electrons coming in for each oxygen that's coming in, then it's consistent with hydrogen peroxide as the final product. Now, in this experiment, each molecule of methylene blue caused the uptake of 50 new molecules of oxygen. Methylene, before it was metabolized and left the body. Methylene blue took an average of 2.7 electrons for every new oxygen molecule that entered the mitochondria on its behalf. Now, these authors suggested that the rate at which methylene blue acquired electrons was underestimated, and that the true value was closer to 4. But if we're looking at the difference between 2 and 4, 2.7 is a lot closer to 2 than it is to 4. And the difference that they're looking for is a difference of 2 electrons. And the difference they find is 0.7 electrons. They would have to underestimate the electron difference by a factor of 3 in order for their hypothesis to be true. Now, further, they didn't account for the other things methylene blue could be reducing. Maybe the extra 0.7 electrons were going to reduce cytochrome C or to reduce iron in the cell, for example. So to me, I see them as assuming their conclusion. They must have underestimated it threefold, because a threefold underestimation is what would be required for their conclusion to be correct. To me, the results are easily consistent with hydrogen peroxide being the exclusive final product. Now, a second study from a group in Hungary using isolated mitochondria taken from the brains of guinea pigs suggested that methylene blue strongly increases hydrogen peroxide production under basically any context, including most of the inhibitors that we looked at previously, except they did not look at oligomycin. Now, without methylene blue, 1.6% of the oxygen was converted to hydrogen peroxide. With 1 micromole per liter of methylene blue, which is roughly twice the concentration expected to be reached in the brain after an acute oral dose of 100 milligrams, so this is probably what you'd reach, for example, on a regular dose of 200 milligrams, this increased threefold to 4.9%. Now, remember here, you're adding methylene blue to get extra oxygen coming in this context. And if you just look at the new oxygen molecules that came in as a result of the methylene blue, every 100 molecules of oxygen coming in because of methylene blue, 11 were converted to hydrogen peroxide. So 11.1% is the rate of conversion of oxygen to hydrogen peroxide when the oxygen comes in because of methylene blue. That's 7 times more than the normal level of 1.6%. So the oxygen specifically elicited by methylene blue is converted to hydrogen peroxide at 7 times the normal rate. In this study, they also showed that the hydrogen peroxide lasts for 2.5 times long as it otherwise would. And that's probably from depleting NADPH used for glutathione synthesis, or glutathione recycling rather. Now, in this study, the authors did not block ATP synthesis. So the other 89 molecules of oxygen presumably entered the respiratory chain to be used in cytochrome oxidase, or also known as complex 4. However, in the Halusi study, it seems quite possible that with blocked ATP synthesis, all of the newly incorporated oxygen was converted to hydrogen peroxide. Now, the Hungarian paper had strongly suggested that methylene blue brings oxygen into the cell in proportion to what is needed to oxidize the fuel. I showed you that data before. Thus, it brings in the number of oxygen molecules that maximize the cell's need, or rather, fulfill the cell's need to oxidize the fuel at hand for the needs for that energy at hand. So if we synthesize these findings together, methylene blue brings in an amount of oxygen that matches the need of the cell to oxidize that fuel in that context. This is converted to hydrogen peroxide at a rate similar to 11% rather than the typical 1 to 2% if the oxygen is used in the respiratory chain. But if the respiratory chain is straight up blocked, then up to 100% of the new oxygen could be converted to hydrogen peroxide. Now, hydrogen peroxide kills microbes. It has hormetic benefits, but it's still ultimately toxic. H2O2 is an important signaling molecule that clearly upregulates antioxidant defenses and probably induces the synthesis of new mitochondria, known as mitochondrial biogenesis. Exercise increases H2O2, and this is thought to mediate part of the fitness response to exercise. And that includes improved antioxidant function and a greater mitochondrial capacity. A direct effect of H2O2 on mitochondrial biogenesis is best shown in the worm C. elegans, and that doesn't necessarily translate to humans, but it offers explanatory power, for example, from the effect of exercise. And it seems not that there aren't other impacts of exercise, like demand for ATP and AMPK and so on. But when you look at the big picture, it looks highly likely that we will find that H2O2 is one of the mediators of the fitness response to exercise through stimulating mitochondrial biogenesis at a physiological dose. And this is in fact the case in C. elegans. Now, the principle that something bad for you can be good for you at low doses by increasing your fitness response is known as hormesis, Hormesis. I covered this in lesson 8 of my antioxidant course and lesson 4 of my energy metabolism course. The activation of a hormetic response is not evidence of health benefit. Cigarette smoking activates hormesis. It's just that it's net toxic. So what we want to look at is the health benefits occur when the net hormesis exceeds net toxicity. If net toxicity exceeds net hormesis, it doesn't matter if something stimulates hormesis because it's more toxic than the fitness response produced to take care of the toxicity. This is the case with things that are poisons. Now, to give an example, an easy way to increase mitochondrial biogenesis in an animal is to make it diabetic. But what happens is the dysfunction of energy metabolism makes hormetic signals such as nitric oxide and hydrogen peroxide. But because of the fundamental defect in energy metabolism, all those signals do is bring you more defective mitochondria. So all you wind up with is more mitochondria that cannot do their job. That is not a health benefit, even though it is an example of a hormetic stimulus causing a hormetic response. It's just that you don't wind up with net hormesis, you wind up with net disease. Okay, so H2O2 is also antimicrobial, and undoubtedly this explains the antimicrobial effects of methylene blue. Go back to first use in medicine was malaria. H2O2 is most effective against pathogens that lack enzymes needed to defend against H2O2. For example, the heme iron-dependent catalase, or the selenium-dependent and glutathione-dependent glutathione peroxidase, both of which convert hydrogen peroxide to water. Methylene blue can get around part of these defenses, however. It inhibits glutathione reductase, at least in part by oxidizing the FADH2 in the active site. As Ehrlich first demonstrated, the dye accumulates much more in malaria-infected red blood cells than in healthy ones, and within those cells, it accumulates especially in the parasite itself. Malaria's own glutathione reductase enzyme is much more inhibited by methylene blue than the human enzyme, even though the human enzyme is also inhibited. Thus, the dye's efficacy against malaria is explained by A, being more toxic to the glutathione reductase of the malaria parasite in the human, and also getting more into the malaria parasite in concentration than into the other uninfected human cells. Thus, as a result of the higher concentration, you have more hydrogen peroxide specifically in the malaria cells. And then as a result of the stronger inhibition and the higher concentration, you get more poisoning of the glutathione reductase enzyme. And so you get that magic bullet effect that Ehrlich was looking for of something that could kill the pathogen without killing the host. Nevertheless, the Hungarian paper found that methylene blue made hydrogen peroxide last 2.5 times as long as it would otherwise in mitochondria that were taken from the brains of guinea pigs. And guinea pigs aren't humans, but guinea pigs are a lot closer to humans than malaria parasites are because they're mammals. In human red blood cells treated with 10 to 100 micromoles per liter of methylene blue, achievable with intravenous use, lipid peroxides elevated 2 to 3-fold if catalase is inhibited. And if catalase is not inhibited, catalase takes care of the job and prevents the lipid peroxides from occurring. Altogether, this suggests that in a healthy person, without some other impairment in their energy metabolism or antioxidant defense, such as someone with glucose 6-phosphate dehydrogenase deficiency, where methylene blue can be harmful, short-term use of standard doses of methylene blue will not create dangerous lipid peroxides, but it will elevate hydrogen peroxide concentrations, perhaps at a hormetic dose. Many animal experiments have suggested that methylene blue has antioxidant effects. As explained in the Hungarian paper, however, these papers use non-specific total reactive oxygen species measurements that are actually way more sensitive to superoxide than to hydrogen peroxide. And the problem with this is that methylene blue is a 2-electron donor. Remember, almost exclusively, you get single electron transfers when you excite methylene blue with light. In the absence of that, methylene blue is a 2-electron donor. It's not going to make superoxide. It's going to make hydrogen peroxide. And so what these papers miss is that even if you rewire the electron transport chain to prevent excessive superoxide production, you still get hydrogen peroxide production from the methylene blue. So yes, there's a net reduction in superoxide in many contexts, but there's always an increase in hydrogen peroxide. Nevertheless, limited evidence suggests that short-term use of methylene blue increases glutathione synthesis through hormesis. Finding number 1. In 1962, after a 2-year-old girl was treated for methemoglobinemia and was with methylene blue and was found to have surprisingly high glutathione levels, investigators injected 2 rabbits with 3 milligrams per kilogram body weight, similar to what's used in the treatment of human subjects with vasoplegic shock, although not adjusted for surface area and other things that we want to make that precise, but relatively similar doses as that. And no control. Their red blood cell glutathione increased more than 3-fold. This effect lasted 10 to 12 days, and it peaked at the 18-hour mark. So with enough methylene blue, you get the glutathione up 3-fold, maxing out at 18 hours. At 18 hours, it starts to fall, but it takes 10 to 12 days to continue falling back to normal. The same authors published a report in 1972 suggesting that this is due to an upregulation of glutathione synthetase, the second enzyme required for glutathione synthesis. Similar results were found in 1977 with 3 rabbits and with using even higher doses and comparing them to 3 controls. So very limited observations, but collectively supportive of the idea that methylene blue increases hydrogen peroxide. Hydrogen peroxide tells the cell that it needs more glutathione, so the cell responds by making more glutathione. That is a hormetic effect. However, this provides little guidance towards understanding what the long-term benefits or harms would be of regular use of methylene blue, because the end result depends on whether the toxicity of hydrogen peroxide outweighs the hormetic response, or the hormetic response outweighs the toxicity. Nevertheless, the hydrogen peroxide offers a very simple explanation of the vast antimicrobial effects of the dye, and that effect is enhanced when you add phototherapy into the mix to generate stronger oxidants such as superoxide singlet oxygen and methylene blue radicals for targeted attacks on pathogens and tumors. Methylene blue causes redox cycling of hemoglobin. Methemoglobinemia is a condition where far more than the usual 2 to 5% of iron in hemoglobin becomes oxidized and thereby loses its ability to carry oxygen. That is, the ferrous iron, also known as Fe2+, becomes the ferric iron, also known as Fe3+. Methylene blue treats methemoglobinemia because Mb+ oxidizes NADPH to become MBH, and MBH reduces Fe3+ back to Fe2+, restoring its oxygen-carrying capacity. Most NADPH comes from the pentose phosphate pathway, which is covered in lesson 27 of my energy metabolism course, and genetic defects in the enzyme glucose-6-phosphate dehydrogenase interfere with NADPH production. In such individuals, methylene blue can fail to fix methemoglobinemia and instead cause hemolytic anemia. The hemolysis is because the NADPH is depleted that is needed for recycling glutathione. The H2O2 cannot be defended against by that glutathione, so it oxidizes the lipids in the cell membrane. The lipid peroxidation makes the membrane fall apart through a lipid peroxidation chain reaction, and the red blood cell contents spill out. The understanding of how methylene blue treats methemoglobinemia, commonly cited in reviews, is that the direction of electron flow makes methylene blue favor Fe2+. However, this interpretation is at odds with recent animal experiments showing that methylene blue protects against the toxicity of cyanide and hydrogen sulfide, in part by causing these chemicals to bind to hemoglobin, reducing their transport into cells. So basically, what you don't want to happen with oxygen, you do want to happen with cyanide and hydrogen sulfide. You want it trapped in your hemoglobin. But these bind to hemoglobin in the oxidized state, whereas oxygen binds to hemoglobin in the reduced state. So if methylene blue is favoring the reduced state to help oxygen bind, how is it also helping cyanide and hydrogen sulfide bind to hemoglobin when they only bind in the oxidized state? This can best be explained not by the direction of electron flow, but rather by the concept of redox cycling. In human red blood cells in vitro, methylene blue accelerates the cycling of the interconversion of hemoglobin oxidation and reduction without making the percentage deviate from the normal 2 to 5% oxidized. However, high concentrations of methylene blue with low concentrations of oxygen can make methylene blue dramatically favor the methemoglobin oxidized state. And this is even worse if the red cells hemolyze. Experiments in sheep show that as methylene blue approaches the lethal dose, it can cause moderate methemoglobinemia. Okay, now let's take a look at the concept of redox cycling. The concept of redox cycling can integrate all these observations. In this concept, methylene blue will oxidize hemoglobin to become the oxidized state, but methylene white will reduce hemoglobin to the reduced state. The reduced state allows oxygen to bind. The oxidized state allows cyanide and hydrogen sulfide to bind. If iron cycles back and forth between the two states, then whichever gas predominates is allowed to swoop in and secure the oxidation state that it prefers. So if the redox cycling is enhanced, the oxygen swoops in to secure the reduced state. But if you have cyanide or hydrogen sulfide toxicity, those gases will also take opportunistic advantage of the redox cycling to secure the oxidized state. Thus, methylene blue speeds the cycling, and that cycling can go perpetually just between methylene blue and iron. It can just cycle endlessly, but you can also have oxidation from the other things in the cell that we know can oxidize or reduce methylene blue. So context matters now. So if you have someone with methemoglobinemia and their hemoglobin is disproportionately oxidized, the concentration of the oxidized form over the reduced form will drive the rates of the reaction towards reducing the hemoglobin until an equilibrium is reached. If you don't have that, you start out with this equilibrium position of a net neutral, accelerated rapid turnover of the hemoglobin oxidation state. Now, the reason that methylene blue is not making the percentage deviate under normal concentrations is because oxygen is there to take advantage of the reduced state. It's not because methylene blue favors the reduced state. It's not even because methylene blue does not favor the oxidized state. In fact, the state that methylene blue would favor at equilibrium is much more oxidized than is healthy. It's just that under normal conditions where you don't have cyanide toxicity or hydrogen sulfide toxicity, you do have oxygen in the air, and the oxygen is what is doing the work in making the hemoglobin stay in the reduced state. Methylene blue is a strong inhibitor of monoamine oxidase A, or MAOA. Several case reports have been published of patients on selective serotonin reuptake inhibitors leading up to a surgery in which they had been treated with intravenous methylene blue, after which they developed serotonin toxicity that was too intense to be explained by their SSRIs alone. This involves tremors, jerks, rigidity, overactive reflexes, sweating, fever, faster heart rate and breathing, dilated pupils, agitation, excitement, and confusion. Methylene blue is a strong inhibitor of MAOA. This is because MAOA is a riboflavin-dependent enzyme. Riboflavin is present as FAD, which oxidizes neurotransmitters to degrade them, becoming FADH2 in the process. MBH, or methylene white, competes with the neurotransmitters, being oxidized to methylene blue, or MB+, instead of them. The concentration required to inhibit 50% of MAOA activity is 164 nanomoles per liter. A single dose of 100 milligrams of methylene blue raises the whole blood concentration to 100 nanomoles per liter for at least 4 hours. Given intravenously, the same dose produces a whole blood concentration of 500 nanomoles per liter. We don't know the brain concentrations in humans, but when rats consume methylene blue orally, they have brain concentrations similar to the blood concentrations that were reached 1 hour after an intravenous administration of the same dose. So if we take that principle, that 1 hour post-intravenous blood concentration equals oral dose brain concentration, then that extrapolation says that when a human consumes 100 milligrams of methylene blue, their brain concentration reaches 500 nanomoles per liter, which is more than sufficient to reach 100% inhibition of MAOA. Since MAOA is responsible for degrading serotonin, dopamine, and norepinephrine, its inhibition by methylene blue is likely to have antidepressant and anti-anxiety effects with increased motivation and opportunity-seeking behavior and some possibility of developing dependence with regular use. This would also suggest that methylene blue carries the possibility for elevated blood pressure when consuming foods rich in tyramine, which is a vasoactive substance in fermented foods that is also cleared by MAOA, or the same possibility when on drugs that stimulate the sympathetic nervous system. Finally, this calls deeply into question whether anyone can use feeling better or the tonic invigorating effect that Shermer had described as an index of an improvement in energy metabolism when using 100 milligrams or more of methylene blue, since this dose would act as a psychiatric drug. Methylene blue inhibits nitric oxide synthase. In rats, injection of 3 milligrams per kilogram body weight methylene blue completely abolished the increase in nitric oxide synthesis that otherwise occurred as a result of an inflammatory breakdown product of bacterial cell walls. It had no effect on a much higher basal level of nitric oxide synthesis. Basal nitric oxide synthesis appears to be protected from methylene blue at this dose because the enzymes that are responsible for it are protected by the cell membranes. By contrast, when you have inflammation, you get inducible nitric oxide synthase, or INOS, which is soluble and is not protected by the membrane and is more exposed to the methylene blue. The mechanism hasn't clearly been demonstrated, but this enzyme requires both a heme iron and a transfer of electrons from NADPH to FAD to oxygen. So redox cycling of the heme or the FAD or depletion of the NADPH would all be plausible mechanisms by which methylene blue could inhibit this enzyme. This is the basis for using methylene blue to raise blood pressure in vasoplegic shock. One non-blinded randomized controlled trial suggested that this halved the rate of death from 7 out of 10 to 3 out of 10 sepsis patients. However, 2 double-blind trials found no effect on mortality, and double-blind is better than not double-blind. In one, 4 people died in each group. In the other, 3 people died in each group. And that study was a study that didn't have a methylene blue-free control, but had 3 different doses of methylene blue. And if you look across those doses, it was 3 in each group, but the number of people in the group varied. And so the percentage was basically 75% in the low dose, 50% in the middle dose, and 60% in the highest dose. There's no dose response. And so overall, it seems very difficult to suggest that this helps with mortality, but meta-analysis suggests it does raise blood pressure, it does raise heart rate, and it does lower the risk of renal failure. So it looks like a net benefit if you survive. The dose-finding trial tested infusions of 1, 3, and 7 milligrams per kilogram body weight and found that the improvements were increased in heart rate and blood pressure. They increased in a dose-dependent manner all the way up to 7 milligrams, but 7 milligrams per kilogram body weight hurt the circulation to the abdominal organs, and so it looks like 3 milligrams is the optimal dose, 3 milligrams per kilogram body weight. The inhibition of nitric oxide synthase is likely to explain the benefits for priapism, the prolonged erection of the penis. It also suggests that it could help with vasodilatory headaches. However, along with the inhibition of MAOA, that's a second reason why methylene blue could raise blood pressure. Mechanistic conclusions. All of this suggests that methylene blue has the following therapeutic properties. 1, it generates hydrogen peroxide. This is antimicrobial. This can be enhanced with phototherapy, which will generate from it superoxide singlet oxygen and methylene blue radicals, which are strongly antimicrobial and anti-tumor. Whether this creates a net hormetic effect in humans over the long term is unknown. Number 2, it causes redox cycling of hemoglobin, which can help treat methemoglobinemia and can offer protection against poisoning from cyanide and hydrogen sulfide. Number 3, it strongly inhibits MAOA. This has antidepressant and anti-anxiety effects. It can serve as a powerful psychiatric drug, and this makes it impossible to know whether feeling better is a result of improved energy metabolism. Number 5, used at high doses intravenously, it inhibits the extra nitric oxide produced during inflammatory insults, which has great value in the case of vasoplegic shock. The inhibition of nitric oxide will most likely explain its use in priapism, prolonged erection as well, and as I said before, suggests maybe it could help with headaches due to vasodilation. Number 6, it rewires the respiratory chain in a number of different ways when the chain is impaired. In none of these scenarios does it lead to a better respiratory chain than the exquisitely designed chain that we naturally possess, but it can offer salvation from lethal toxins, and it has a major benefits most likely has major benefits for genetic defects in the respiratory chain. With that said, are any of these things that we want to enlist as part of our everyday life? That depends on whether we see it as a net hormetic benefit that should be added to our toolkit of fitness inducers. Is methylene blue fundamentally hormetic? The concept of hormesis is that as dose of something increases, at the low dose, you go into the range of net benefit. But as you increase the dose further, you lose the net benefit. And eventually, if you keep increasing the dose, you get into harm. The best way to explain this would be a toxin that at low doses stimulates a fitness response, but at high doses, its true colors show and you get net harm. Brucci and Gonzalez Lima of the University of Texas at Austin published a paper arguing that methylene blue is hormetic. Using a dose response approach where the ideal dose is small and a high dose is worse than no dose at all, they gave several examples, and these are the ones that I find most convincing. Number one, incubation of rat brain tissue with 0.5 micromoles per liter increased cytochrome oxidase activity, which is often taken as an index of a hormetic increase in mitochondrial biogenesis. 5 micromoles per liter had no effect, and 10 micromoles per liter caused it to fall. Okay, number two, injecting rats with 0.05 to 1 milligrams per kilogram body weight right after a memory training session enhanced later recall, but 5 milligrams had no effect at all, and 10 milligrams caused amnesia. Injecting rats with 4 milligrams per kilogram increased wheel running behavior, but 10 milligrams per kilogram had no effect, and 50 to 100 milligrams per kilogram lowered wheel running behavior. Finally, there's a study in the elevated plus maze. This is a maze where the rat has a home base, and then there is a narrow corridor that is raised so that the rat's fear of heights is activated that they can run on as a maze to try to find food. And this is considered an index of anxiety because if the rat spends more time in home base because the rat is afraid of the heights, then the rat's anxiety levels are higher. But if the rat is more likely to explore and go out looking for food, then it's taking more risk-seeking behavior, and that indicates a lower level of anxiety. So in an elevated plus maze, injection of rats with 7.5 to 15 milligrams per kilogram caused an increase in time spent in the risky part of the maze, while 30 milligrams per kilogram had no effect and 60 milligrams per kilogram decreased the time spent in the risky part. At surface level, what this looks like is the low dose is anti-anxiety and the high dose is pro-anxiety. However, at the high dose, the spontaneous locomotor activity of the rats was decreased in general, which confounds the inference that they had higher anxiety. They may just not have been able to move. And this is consistent with the previous study showing that those doses decrease wheel running behavior. And it's also consistent with the fact that these are approaching the doses that kill sheep. And if the doses kill sheep, they're probably causing toxicity. And so you would expect poisoned energy metabolism at these doses. Okay, now let's try to synthesize this. In rats, 1 milligram per kilogram injection results in 0.5 micromoles per liter in the brain tissue. So the dose that improves memory when it's injected immediately after a training session aligns well with the concentration that appears to cause a hormetic increase in mitochondrial biogenesis in the brain. Okay, it sounds nice up until there, and now it gets kind of not so great. Okay, so the minimum dose that causes an increase in wheel running is in the range that abolishes the memory benefit of the lower dose. And the minimum dose that suppresses anxiety aligns with the dose that causes amnesia, likely by causing mitochondrial dysfunction in the brain. So the data do suggest that methylene blue has hormetic effects, but it's absolutely horrible as a general purpose hormetic to apply across these concepts. It's not a hormetic towards energy and memory and anxiety and physical activity. It's a hormetic with respect to the memory effect, and that's it. Because at the doses required to get any benefits to the other things, you're giving yourself amnesia. So most likely, the genuine hormetic effect is from hydrogen peroxide causing mitochondrial biogenesis in the brain, which is helping with the memory. But the increased wheel running and risk-taking behavior is probably from the psychiatric monoamine oxidase inhibition. This monoamine oxidase inhibition gets greater and greater until you get to the point where you would have killed 50% of the sheep. And that's when you get it counteracted by poisoned energy metabolism that is basically maybe the animal doesn't have any monoamine oxidase activity, but it also doesn't have any respiratory chain left, and so it's not moving. So the only clear example of hormesis in my eyes is an increase in mitochondrial biogenesis. However, this was not compared to other hormetic stressors such as exercise or eating polyphenol-rich fruits, vegetables, herbs, and spices, which also cause an oxidative stress-related hormetic response. And so I don't see how we can look at this and say that methylene blue is something to add to the toolkit of hormetic stresses when we already have great hormetic stresses. And there's no evidence that this adds to them or synergizes with them. Methylene blue fails in Alzheimer's and causes a very worrisome side effect. There's one phase 2 trial lasting 6 months and 2 phase 3 trials lasting 15 months that have tested formulations of methylene blue for Alzheimer's that have failed to support its efficacy, leading to quite a bit of hand-waving to explain away the negative results. The doses in trials range from 69 to 250 milligrams per day. The placebos contain 8 milligrams per day in order to turn the subject's urine the same color. So actually the placebos had methylene blue 8 milligrams per day. So we can call them placebos with quotes. As I already covered, 100 milligrams orally would be likely to produce 0.5 micromoles per liter in the brain, and this would correspond to a dose of 1 milligram per kilogram in the rat. So these treatment doses are right in line with the research on mitochondrial biogenesis and enhanced memory from hormesis in the rat studies. The main difference is the rat studies were acute single doses, and these are 6 to 15 month trials of daily doses, and that we're looking at humans instead of rodents. Now, an observational study that was nested in the 2 phase 3 trials took the data on when the people came in for the first day and took their first dose, how did the methylene blue concentration rise in their plasma? And remember, the placebo groups got 8 milligrams of methylene blue, so they all have data on a methylene blue response to the so-called placebo. So what they did was they took they plotted, as I'm showing on the graph for the video, they plotted the maximum concentration 3.5 hours after the dose for each person against the improvement in cognitive function at the end of the trial. And what they showed was that between 0.3 and 0.5 nanograms per liter methylene blue plasma response, you had a linear increase in the cognitive scores at the end of the trial. So they argued, actually what we want is methylene blue concentrations in basically the plateau range of the placebo group. Okay, then they classified the placebo group into 4 groups of responders, whether they were low, quartile 1, quartile 2, 3, 4, in terms of how much did the methylene blue rise after they got the placebo. And they compared them to the treatment group. And they looked at, in panel A, cognitive function at the end of the study, in panel B, daily living at the end of the study, and in panels C and D, indices of brain volume at the end of the study. And what you see is that the treatment groups were better than the lowest responder placebos, but they were worse than the highest responder placebos in every case. And so what they argue is that the optimal dose for all of these treatment effects was the placebo. Now, this deserves to be tested in a future trial, but there's no evidence whatsoever that the plasma response caused the improvement in cognitive benefits or any of the other benefits. And they provide no discussion of why someone would have a higher plasma response. This could be due to better intestinal absorption, slower accumulation in the brain, or slower loss in the urine. But back up, what did I say? slower accumulation in the brain, let's just say that the methylene blue stayed in the plasma instead of getting rapidly taken up into the brain. If this relationship is due to slower accumulation in the brain, all this study shows is that the people with the best outcomes were the people that had the least methylene blue in their brains. However, what I find concerning is the adverse events in these trials. And it's mainly the single phase 2 trial. But let's go through the trials starting with phase 3. So in the first phase 3 trial, there was a dose-dependent effect on people dropping out of the trial. 24% in the 8 milligram so-called placebo, 31.3% in the 150 milligram group, and 38.3% in the 250 milligram group. These are massive dropout rates. Gastrointestinal and urinary problems were the most common side effects. In the second phase 3 trial, 5 times as many people dropped out in the treatment group, which was 200 milligrams, compared to the 8 milligram placebo group. And again, the most common increased side effects were gastrointestinal and urinary. The earlier phase 2 trial had 4 times as many treatment subjects drop out, 31.4%, as 8 milligram so-called placebo subjects, 7.6%, over the course of 24 weeks. Consistent with the phase 3 trials, gastrointestinal side effects, mainly diarrhea and urinary side effects, mainly an alternation in urinary output, were the prime drivers. However, the phase 3 trials found no difference in injuries from falls, while the phase 2 trial found a large increase. Only 1.1% of the 8 milligram so-called placebo participants reported an injury from falling. By contrast, this rate was 8.5% in the 60 milligram group, 5% in the 120 milligram group, and 5.6% in the 200 milligram group. Although there's no difference in the 3 treatment doses, all of them are dramatically higher than the 8 milligram so-called placebo group. And if you pool them together, you have 6.1% reporting injuries from falls in the treatment groups, which is 5.6-fold greater than in the 8 milligram so-called placebo group. Now, I don't know why the phase 2 and phase 3 trials differ. One difference is that the average age was 74 in the phase 2 trial, and the average age was 70 in the other 2 trials. The variation around those means was similar in all 3 trials. So the basic difference is phase 2 is shifted up 4 years. Now, 4 years might mean a lot when you get into the 70s in terms of the propensity to fall. And so that makes me wonder whether the older age made the phase 2 trial more sensitive in picking up subtle signs of declines in neuromuscular function as a result of the treatment. Now, we have to go back to the animal cellular and subcellular studies to understand why this appeared to have no benefit and to have caused harm to at least some of the people. So remember 3 things. Number 1, the net hormetic cognitive benefit has only been shown for acute doses in animals, and the mechanism is likely a highly nonspecific effect of hydrogen peroxide provided to animals that did not have other hormetic stressors that might have been good replacements for humans, such as exercise and vegetable-rich diets. Number 2, if you short-circuit the respiratory chain for no reason, you'll decrease ATP synthesis. And then number 3, if you plant something in the middle of the respiratory chain, like we were talking about at the beginning, if you overfeed complex 2 without enough ADP from exercise, you will get more reactive oxygen species, more superoxide from reverse electron transport. And methylene blue, in the context of overfeeding complex 2 on something like fat and leucine, in the context of no ADP, such as not exercising, can cause reverse electron transport. So across contexts, you're likely to get decreased ATP. And in the context of someone on a high-fat, low-carb diet who's not exercising, you're likely to get reactive oxygen species from reverse electron transport. And then in all of those contexts, you increase hydrogen peroxide production. And so reverse electron transport will give you superoxide, but you will always get hydrogen peroxide from methylene blue. The main problem with these trials is that they were taking a common disease and trying to treat it with something that is best suited to treat specific respiratory chain disorders, rather than looking at which of the Alzheimer's participants had signs of an impaired respiratory chain at specific complexes. They just gave it to all of them. And I think that is the primary culprit in the failure of the Alzheimer's trials. Whether methylene blue helps or hurts depends on whether you need it. Buried into the tables and figures of the animal experiments showing benefits of methylene blue are signs that I see as signs of trade-off. So I already showed you the data from the oligomycin paper that shows that the decrease of ATP that you get with methylene blue when you don't need it is as strong as the increase of ATP that you get with methylene blue when you do need it. Now, in another study, they injected into the brains of rats rotenone to injure a specific part of the brain, the striatum, that is involved in Parkinson's disease. Now, in the diagram that I'm showing you, this is demonstrating how they looked at the different parts around the injury. So the greatest damage is where they injected the rotenone, and that is called the lesion core. The area around that has a more moderate reverberation of damage is called the penumbra. The undamaged part of the brain on the same side as the lesion is called the ipsilateral side. And then, not shown in the diagram, the other side of the brain is called the contralateral side. They looked at cytochrome oxidase activity in these different regions. And what they found was that in the core, rotenone decreased it and methylene blue rescued it, partially rescued it. But in the penumbra and the contralateral side of the striatum, methylene blue just straight up decreased the cytochrome oxidase activity in those two regions. So that shows you that in the case of a specific injury, you're getting an improvement in metabolism in the area where you were injured most, but you're getting a similar decrement in metabolism in the areas that you were not injured. Again, if you need it, it helps. If you don't, it hurts. The last study that we'll consider is about sodium azide. Sodium azide is a complex 4 inhibitor used in airbags as an explosive, as a preservative in hospitals and laboratories, and as an agricultural pesticide. Complex 4 activity is decreased in Alzheimer's in an area of the brain called the posterior cingulate cortex. So perhaps spending more time in hospitals and eating conventionally grown food increases the risk of Alzheimer's. These authors directly infused sodium azide into the posterior cingulate cortex to try to mimic the Alzheimer's effect. And they showed that it hurt their memory based on their ability to remember where food was located. Methylene blue fully corrected the amnesia. In fact, their memory was slightly better with methylene blue and sodium azide than in the untreated control, although the difference was not statistically significant. Despite this, methylene blue actually worsened the decrease in cytochrome oxidase activity, and I think this is probably because it was helping reroute around the defect. Sodium azide disrupted the normal functional connectivity of the posterior cingulate cortex, and methylene blue corrected this. But what concerns me is an apparent trade-off in the functional connectivity among brain regions outside the site of the injury. In the thalamus, the sodium azide increased the functional connectivity, and methylene blue brought it down even lower than it was at baseline. So it appears to have overcorrected it. In the medial temporal lobe, sodium azide non-significantly tended to increase connectivity there, and methylene blue seemed to enhance that, and it became statistically significant. But what I really find concerning is that sodium azide had no effect on the functional connectivity in the visual motor loop, and methylene blue dramatically decreased the functional connectivity in that region. Now, the authors claimed that this was adaptive reconfiguration induced by the methylene blue rather than a general and non-specific metabolic enhancing effect, but they didn't discuss in any detail how it would have served the improvement in memory and offered no discussion on whether it constituted a trade-off with respect to other skills. I emailed the corresponding author 8 days before I made this. I didn't hear back. Granted, the paper is 11 years old, so maybe it didn't get through. Another paper gives the following real-world description of the importance of visual motor connectivity. Everyday functioning requires the ability to continually adapt motor output according to visual feedback. The integration of visual and motor functions is utilized in everyday tasks ranging from relatively simple, such as grasping an object, to a more complex, like driving a car. As an example, vision is used to locate an object and determine its relative size and distance. This information is then implemented to guide our hand to the correct location and adjust our hands to form the correct group for that object, whether it's a spoon and we make a pincer grip, or for an individual to pick up an individual piece of cereal, or a full-handed grip to pick up a water bottle. When driving, we continuously use our vision to monitor the surrounding traffic and road conditions, integrate this information with our motor system to control the steering wheel, accelerate or brake to safely maneuver the vehicle to our end destination. Both of these examples are tasks that involve visual motor integration, which is defined as, quote, the coordination of neuronal activity between visual-related and motor-related parts of the brain in order to influence behavior and perception. This is sometimes tested in rodents by training them to turn right or left after seeing specific images on a screen. When I think of this, I wonder if it could explain the 5.6-fold increase in the reports of injuries from falls in the phase 2 Alzheimer trial on treatment levels of methylene blue. Natural alternatives for hormesis and for rewiring the respiratory chain. The hormetic benefit of hydrogen peroxide is best obtained through exercise, where physiological sensations of fatigue create natural limits around the tolerance for the hormetic stimulus and encourage natural resting behavior to recover in between bouts. As covered in Lesson 8 of my antioxidant course, polyphenols that are especially rich in vegetables, fruits, herbs, and spices are the, quote, beneficial toxins that create an oxidative stress stimulus to ramp up antioxidant defenses. These are the toxins that we became adapted to long before 1876, and our systems are exceedingly capable of regulating their absorption, detoxification, and clearance. True, not everyone tolerates them, but do we have better evidence that the average person thrives on methylene blue? Of course not. While methylene blue can rewire the respiratory chain, it has no brain to know that it's doing the right thing. Judicious analysis of laboratory data and making human choice can arrive at a more specific strategy. Complex 1 blocks can be aided by avoiding complex 1 poisons like metformin and berberine, and can otherwise be rerouted by feeding complex 2. That means fatty acids and leucine and disodium succinate can be used to disproportionately feed complex 2. Some complex 1 disorders will respond to riboflavin in high doses. Complex 2 blocks can be aided by eating a low-fat, minimally adequate protein, high-carb diet to disproportionately feed complex 1, and they also may respond to riboflavin. CoQ10 deficiencies can be aided by supplementing CoQ10. Complex 3 blocks can be aided by feeding complex 4 directly with near-infrared light in the 700 to 1000 nanometer range, which you don't really get from the sun, but you'll get more from a fire. High-dose vitamin C and MK4, as described in several case reports that are linked in the written version of this, or by using S-adenosylmethionine to stimulate transsulfuration and molybdenum to make sure that sulfite can feed its electrons directly to complex 4, and sulfur amino acids to provide plenty of that sulfite in the form of L-cysteine, N-acetylcysteine, L-methionine, or a combination of those. And that will activate the conversion of homocysteine to cysteine, which will then have the excess over what is needed for glutathione go into sulfate on the path there. It goes through sulfite. And although molybdenum is needed to clear sulfite, molybdenum does that by helping calories from oxygen in the air, believe it or not, join to the sulfite and have that chemical energy delivered directly to complex 4 of the electron transport chain. Complex 4 blocks can be aided by avoiding sulfur amino acids and other forms of sulfur by making sure copper and iron status are both adequate. Complex 4 hypoactivity compromises hydrogen sulfide clearance, which inhibits short-chain fatty acid metabolism, so a low-fat diet may also be needed to help. And now we come to the home stretch. Who should use methylene blue? Methylene blue is a monoamine oxidase A inhibitor and carries the risk of serotonin toxicity, hypertension, and dependence. Contraindications include glucose 6-phosphate dehydrogenase deficiency, use of SSRIs, hydroxylamine toxicity, renal failure, and caution should be used in cases of methemoglobinemia caused by dapsone or aniline. and methylene blue can make a pulse oximeter inaccurate. With these contraindications out of the way, where is it useful? Well, methylene blue is extremely poorly suited to act as a general hormetic stress, and it does not in any way, shape, or form act as a general mitochondrial tonic for improvements in general mitochondrial health. Methylene blue does make an effective antimicrobial, and it's probably safer than most antibiotics in the sense that most antibiotics are mitochondrial toxins, and methylene blue is at least an antidote to some mitochondrial toxins. As covered earlier, the primary uses are 50 to 250 milligrams a day for inherited methemoglobinemia, intravenous use for acute methemoglobinemia, intravenous use before, during, and after surgery to prevent or treat vasoplegic shock, local use during surgery to prevent post-surgical tissue adhesion, 12 milligrams per kilogram body weight twice per day orally for 3 days to treat malaria, disc injections for discogenic back pain, and internally or locally applied or injected in conjunction with phototherapy against superficial infections or skin cancer. It is very effective as a topical disinfectant. Doses between 8 and 250 milligrams per day are reasonable to try as a short-term treatment for headache mediated by vasodilation. Doses between 100 and 200 milligrams a day are likely to be highly effective monoamine oxidase inhibitors with activity against anxiety and depression, but with risk of serotonin toxicity, high blood pressure, and psychological psychiatric dependence. Methylene blue has promise, but needs more study as an antidote to toxicity from rotenone, sodium azide, cyanide, and hydrogen sulfide. If genetics or highly specific exposure to a single mitochondrial toxin is at the root of a respiratory chain disorder, methylene blue should be considered as an experimental therapy. This should be tested using MitoSwab Plus, which allows you to see which complex is defective if there's a defect. However, prior to the MitoSwab, I highly recommend a comprehensive nutritional screening, see the link in the description, to rule out deficiencies of the many nutrients involved in the respiratory chain, but especially of riboflavin, CoQ10, and copper, each of which could have a somewhat misleading appearance as being a disorder of complex 1 in the case of riboflavin, anything with an assay ending in complex 3 as in the case of CoQ10, or complex 4 as in the case of copper. If such defects are found, the more natural methods that I just covered should be tried first, and I'll cover those in more detail in the future in protocols. Methylene blue likely has the best promise for disorders of complex 4, and some degree of utility for disorders of complex 3. And this is because it gets progressively harder to do something about the respiratory chain that is effective and natural as you move down the chain. Complex 1 and 2 is easy to manipulate with macros. Carbs go to complex 1, fat and to a lesser extent protein go to complex 2. So manipulate the macros according to which complex works better. That's easy. Complex 3 may respond to supraphysiological doses of some supplements, but you can't really manipulate your macros around it. And complex 4 is difficult to get around above all because the fundamental use of oxygen can be compromised. And if that's compromised, you really cannot get around it and have a functioning respiratory chain. Nevertheless, methylene blue can even short circuit complex 4 by taking that oxygen that wants to go to complex 4, converting to hydrogen peroxide, and allowing some activity to go through. Once nutritional deficiencies are ruled out and the specific disordered complex is identified, methylene blue titrated up slowly from 8 milligrams to 250 milligrams per day can be tried, generally in at least 2 divided doses, with the key metrics being home measurements of glucose, ketones, and lactate, with the central metric being keeping lactate on the lower end of the 0.5 to 1.5 millimoles per liter range whenever you are not engaging in zone 2 or higher exercise. We have now arrived, finally, at the end of this presentation. What's your experience with methylene blue? Did this change your mind about anything? Let me know in the comments.